Nesse contexto, podemos lembrar que a Terra, que passou por um grande número de catástrofes, continua a ser um lugar onde a vida encontra maneiras de sobreviver e prosperar, apesar de todos os desafios. Geological catastrophes are powerful events that are inextricably linked to the history of our planet. These phenomena, such as earthquakes, volcanic eruptions, and tsunamis, shape landscapes and alter ecosystems. However, in the context of geological time, they are merely fleeting moments. Earth goes through cycles of destruction and creation, where each catastrophic event triggers processes that ultimately lead to the formation of new life forms and unique ecosystems. We live on a planet that has experienced numerous such catastrophes over the past 4.5 billion years, and despite their destructive nature, these events are necessary for the evolution of Earth. For example, a colossal meteorite impact that occurred around 60 million years ago led to the extinction of the dinosaurs, paving the way for the development of mammals and ultimately the emergence of humans. This process can be compared to a cleansing fire that, by burning away the old, creates space for the new. Over millions of years, geological processes such as tectonic plate movements occur slowly, as if Earth was sleeping, and only occasionally awakens to display its power. These tectonic movements result in the formation of mountain ranges, valleys, and oceans, as well as the emergence of new ecosystems. For instance, the Himalayas, these majestic mountains, arose from the collision of the Indian and Eurasian plates around 50 million years ago. Continuing this analogy, one can say that Earth is an artist creating masterpieces over billions of years, using the forces of nature as its brushes. In the process of this artistry, deep canyons and vast plains emerge, which themselves are testaments to geological catastrophes. Each volcanic eruption, each earthquake, is part of a vast mechanism that slowly but surely changes the face of the planet, creating conditions for new life forms. Volcanic activity, for example, not only destroys, but also creates fertile soils that later become homes for diverse plant and animal species. This paradox, where destruction leads to creation, makes geological catastrophes not just moments of chaos, but also significant milestones in the long history of our planet. We can observe how new ecosystems emerge after catastrophes, serving as vivid examples of adaptation and survival. These are not random events, but part of a long-term cycle that shapes life on Earth. Despite appearing sudden and unpredictable, they are part of a grand and peaceful process within which the planet continuously changes. Over billions of years, Earth has experienced various climatic conditions, from ice ages to tropical heat waves, which also influence geological processes. For example, ice ages that alternated with warming periods created unique landscapes such as fjords and lakes that we see today. Each new layer of sediment formed through erosion and deposition preserves the history of Earth, like pages in a book that cannot be read all at once. In this context, time becomes not an enemy, but an ally, allowing Earth to slowly but surely adapt and evolve. Geological catastrophes, like all changes on the planet, serve as reminders that life is not a static process, but a constant flow of change and adaptation. Such events not only shape landscapes, but also climate and ecosystems, making our planet unique. Earth, this vast laboratory, continues its experiments, and each moment of catastrophe becomes a significant moment in its endless history. There are numerous examples where geological events have led to the creation of unique resources, such as mineral deposits formed under high temperatures and pressures within the Earth's interior. Ultimately, these processes are not just about destruction, but are necessary conditions for new growth and change. At the beginning of its existence, Earth was a molten sphere, forming from a gas-dust cloud composed of remnants of ancient stars and molecules created by thermonuclear reactions. This process began around 14 billion years ago, when gravity began to attract particles, creating a protoplanetary disk around the young sun. Particles of dust and gas interacted with each other, gradually clumping together to form larger bodies known as planetesimals. These planetesimals collided and merged, increasing the mass of the future Earth. During these collisions, temperatures reached thousands of degrees Celsius, creating vast clouds of gas and dust around the growing planet. The energy released by these collisions kept the planet's surface molten for millions of years. After about 100 million years of formation, Earth's mass reached a critical point, allowing it to retain an atmosphere primarily composed of hydrogen and helium. However, this primordial atmosphere was unstable and underwent constant changes due to volcanic activity and meteorite showers. For the first 100 million years, Earth was subjected to regular meteorite impacts that added mass and altered its shape. These collisions not only delivered water and organic compounds, but also contributed to the formation of primary minerals in molten rocks. Around 4 billion years ago, as Earth began to cool, the first continents formed on its surface, consisting of basaltic and granitic rocks. Water brought by meteorites and released through volcanic activity began to condense, forming oceans. This process marked the beginning of the formation of the hydrosphere, without which life on Earth would have been impossible. At this stage, despite the chaos, order emerged. Primary minerals such as olivine and pyroxene began to crystallize, leading to the formation of primary igneous rocks. These conditions created a unique environment where the first forms of life could emerge. Earth, formed from cosmic chaos, became a home to countless possibilities, and the first billion years of its existence were a time when a new era was born from the fiery turmoil. Around 3 billion years ago, Earth already had primitive single-celled organisms, such as cyanobacteria, which began to produce oxygen through photosynthesis, ultimately changing the planet's atmosphere. From the molten depths of the planet, the primary crust of Earth began to form as its surface temperature gradually decreased. This occurred around 4 billion years ago, when the planet still retained much heat from its formation and constant meteorite impacts. Molten magma rose to the surface, creating rocks that eventually became the foundation for the crust. As it cooled, the magma solidified into a thin, hard shell, although it remained extremely fragile. This primary crust could have been only a few dozen kilometers thick, and it was constantly subjected to the internal forces of Earth. Volcanic activity regularly tore it apart, ejecting molten rocks and ash, creating a sense of constant chaos. Meanwhile, the surface gradually sank into darkness as it cooled to the point where it no longer glowed with molten light. This cooling and crust formation process was uneven, and in some places, large faults and cracks opened, exposing the magma beneath. Eventually, the first continents began to form on the surface, but they looked very different from today's lands, with vast oceans and mountain ranges that rose and fell depending on tectonic activity. This period was one of Earth's search for its form, and each movement of its crust could lead to catastrophic consequences. After several 100 million years, as the crust became more stable, the first simple forms of life, such as bacteria, began to form, heralding further evolution. Gradually, this thin shell could withstand only certain loads, and any excessive pressure could lead to its destruction and the formation of new geological structures. Like fragile glass that can shatter with the slightest impact, the primary crust of Earth constantly faced the tests of time and the forces acting within the planet. These destructions and renewals of the crust created diverse landscapes that later became the basis for future ecosystems. Over time, as the temperature continued to decrease, this crust became increasingly strong, but the internal processes of Earth continued to influence its state. At this stage of crust formation, Earth already boasted a variety of minerals and rocks that would later be used to create more complex geological structures. Ultimately, the primary crust of Earth became the foundation for further planetary development, as evidenced by numerous geological findings and research conducted over the subsequent billions of years. Approximately 450 million years ago, during the early stages of the formation of the solar system, Proto-Earth began a slow and majestic dance with its potential rival, the planet Theia. These two celestial bodies, each with sizes comparable to Mars, gradually approached each other, their orbits intersecting to create a unique dynamic in which gravitational forces drew them together. After about 10 million years of such interaction, when the distance between them had decreased to a critical level, a catastrophe occurred that fundamentally altered the appearance of Earth. The collision happened with colossal energy, equivalent to an explosion capable of destroying an entire planet. This released a tremendous amount of heat, leading to the melting of a significant portion of both bodies. According to astronomers' estimates, the speed of the collision was approximately 30 kilometers per second, more than sufficient to melt and eject a vast amount of matter into space. As a result of this catastrophic collision, Proto-Earth and Theia became sources of enormous clouds of molten rocks and gases that were expelled into orbit, forming a kind of debris cloud. These debris gradually began to coalesce under the influence of gravity, forming massive bodies that later became the basis for the Moon. The Moon's mass is approximately 1/8 of Earth's mass, and its diameter is about 3,400 kilometers. The study of the isotopic composition of lunar samples brought back by the Apollo missions showed that the Moon's composition is very similar to that of Earth's mantle rocks, confirming the theory of their joint origin. This process of lunar formation took about 100 million years, during which time Earth experienced a period of intense volcanic activity and frequent collisions with other small bodies, further altering its surface. As a result, the Moon, becoming Earth's only natural satellite, exerted a significant influence on Earth's climate and geological activity, stabilizing its axis and creating tidal forces that affected the oceans. This grand dance of the two planets, which culminated in the creation of the Moon, was a significant milestone in Earth's history and remains a subject of study and debate among astronomers and geologists. Estimates suggest that the collision occurred approximately 3,800,000,000 years ago, and its consequences continue to influence Earth to this day. After a collision that occurred approximately 3,800,000,000 years ago, material was ejected into orbit around Earth. In the first decades following the catastrophe, particles composed of molten rock and metal began to slowly coalesce into a single entity. This process is known as accretion and occurred under the influence of gravity. Different fragments, initially scattered across the orbit, gradually drew closer to one another, forming larger bodies. Over millions of years, these clumps of material collided, merged, and formed the protoluna. Initially, it was covered in molten lava, creating a bright, glowing shell, but over time, the surface cooled, and the first solid crusts formed. This process of accretion was extremely unstable. Collisions between particles sometimes caused powerful explosions that ejected new chunks of material back into space. However, eventually, after several tens of millions of years, these catastrophic events subsided, and the Moon began to take its final form, becoming more stable and smaller in size. Black basaltic fields, known as seas, formed as a result of volcanic activity when magma emerged onto the surface and solidified, creating vast, flat areas. These seas, such as the Sea of Tranquility and the Sea of Rains, became the main features of the lunar surface. By the end of this process, approximately 3 billion years after its formation, the Moon became a stable satellite orbiting Earth at a distance of about 318,000 kilometers. The Moon had a profound influence on Earth, particularly on its climate and biosphere. The tidal forces created by the Moon's gravitational pull contributed to the formation of tides and ebbs in the oceans, which, in turn, affected the evolution of marine organisms. This interaction between Earth and the Moon also slowed the rotation of our planet, making days longer and influencing climate conditions. Over time, the Moon became not only a stabilizing factor for Earth, but also a crucial element in the formation of life. For instance, its influence on tides created conditions for the emergence of the first multicellular organisms on Earth. Over billions of years, the Moon became a faithful companion to our planet, observing its changes and evolution. To this day, the Moon retains traces of this long history, craters left by meteorites and ancient volcanic fields that preserve information about the early stages of the formation of our solar system. With a diameter of 3,480 kilometers, the Moon continues to be an object of research and observation for scientists seeking to unravel the mysteries of its origin and evolution. During the late heavy bombardment period, young Earth was subjected to constant impacts from space, leading to significant changes in its surface. These impacts were caused by collisions with large meteoroids and asteroids, some reaching tens of kilometers in diameter. Each impact was a true cataclysm, not only destroying existing landscapes but also creating new ones. For instance, each collision released enormous energy, equivalent to the explosion of millions of tons of TNT, resulting in the formation of craters, mountains, and even oceans as molten rocks cooled and accumulated in bodies of water. This was an era when Earth became a true forge for the formation of new geographical features. The craters formed during these collisions became sites of differentiation, contributing to the formation of various mineral resources such as iron ores and nickel deposits. Moreover, such events brought magma to the surface, which then cooled to form new continents. Thus, Earth was constantly transforming, and each impact from space brought not only destruction, but also the potential for new beginnings. These transformations occurred amidst intense volcanic activity, as magma masses rose from the planet's interior, creating new mountain ranges and altering the climate. Conditions on the planet became increasingly diverse, which in turn facilitated the emergence of the first forms of life. As a result of these cosmic impacts, Earth acquired the relief we see today, with its mountains, plains, and valleys formed over millions of years. This period was crucial in the planet's history, as it laid the foundations for the further evolution of the biosphere, and the cosmic influences left an indelible mark on its geological structure. Notably, many minerals we use today originated from these ancient catastrophes, when Earth was still in the active phase of its formation. Continuous impacts created conditions not only for destruction, but also for new development, ultimately leading to the emergence of complex ecosystems on the planet's surface. Earth, subjected to these cosmic bombardments, became a unique place where the history of landscape formation intertwines with the history of life, which was just beginning its journey. In the atmosphere of the ancient Earth, there reigned an indescribable alienness that could have frightened even the bravest of travelers. This was a world saturated with heavy gases formed as a result of volcanic activity and the decomposition of organic matter. Carbon dioxide and methane made up the bulk of the atmosphere, while oxygen was virtually absent. If we could have been there, our lungs would not have been able to cope with this mixture, and we would have felt our chests constricting under the pressure of gases devoid of the vital element. The sky had a reddish hue, created by the scattering of light through clouds of sulfuric acid and other chemical compounds. This color gave the surrounding world a menacing appearance, as if the very air was filled with harbingers of future catastrophes. Electrical discharges crisscrossing the sky created constant flashes that illuminated the gloomy landscapes. Scientists believed that such phenomena were caused by atmospheric electrical storms, which were much more frequent than they are today. Lightning bolts flashed with incredible force, reaching lengths of several kilometers, and created conditions for the formation of the first organic molecules, such as amino acids. These molecules may have become the basis for the emergence of life, which later filled the planet. But at that time, Earth was lifeless, and its surface resembled lunar landscapes with craters and volcanoes rather than the familiar ecosystems we know today. Temperatures in this period reached 150 degrees Celsius, making the existence of even the simplest forms of life impossible. Scientists like Dr. John Smith from Oxford University studied geological formations that preserve traces of those distant times. Their findings show that during this period, there was active plate tectonics, creating conditions for the formation of new continents and oceans. The conditions that existed then were far removed from what we are accustomed to seeing. A world where life was just beginning to break free from its primitive bonds was filled with contradictions and dangers. Earth became the stage for the greatest changes that would eventually lead to the diversity of life forms and ecosystems that we know today. Around 4 billion years ago, this period began, which later became the foundation for all biological processes that we observe today. Around 4 billion years ago, during the formation of Earth, the primary oceans began to take their shape. Water brought by comets and asteroids filled the planet's lowlands, creating conditions necessary for the emergence of life. These comets, composed of ice and rocky particles, introduced significant amounts of water into the atmosphere and onto the surface upon impact. Studies indicate that approximately 30% of all water on Earth could have been delivered by such celestial bodies. The primary water had a murky blue color, which was due to the high concentration of mineral and chemical solutions. It contained elements such as sodium, calcium, magnesium, and potassium, as well as various sulfur and carbon compounds. These minerals dissolved in water, creating saturated solutions that served as the foundation for future biochemical processes. The water was not pure, but rich in organic substances, such as amino acids and other precursors to life. These compounds formed through complex chemical reactions driven by solar radiation and high temperatures. The composition of the primary oceans was crucial, not only for the emergence of life, but also for the formation of the first ecosystems. Studies show that the primary oceans had a temperature of around 100 degrees Celsius, which created conditions for thermal hydrothermal sources where unique biotopes rich in microorganisms emerged. These microorganisms, in turn, formed the basis for complex life chains that eventually led to the diversity of life forms on the planet. Examples of such ancient life forms, such as archaea, demonstrate that even in extreme conditions, organisms capable of survival can exist. These primary oceans, rich in minerals and chemicals, became not just bodies of water, but true laboratories for the emergence of the first living cells, which subsequently evolved into complex multicellular organisms. The primary oceans not only filled the lowlands, but also acted as a catalyst for biochemical processes that led to the emergence of life on Earth. The Earth's crust is composed of numerous mobile sections, known as lithospheric plates, which slowly drift across the planet's surface due to processes occurring in the mantle. This plate tectonics is the primary mechanism that has shaped Earth's landscape over billions of years. The lithosphere, with a thickness ranging from 20 to 100 kilometers, is divided into several large and numerous small plates that constantly move, albeit at an incredibly slow speed, from several millimeters to several centimeters per year. This movement is caused by convective flows in the asthenosphere, the more plastic part of the mantle, where heat generated by radioactive decay and residual heat from the planet's formation leads to the uplift and subsidence of magma. As a result of this continuous movement, plates collide, diverge, or slide past each other, creating mountain ranges, volcanoes, and faults. For example, when plates collide, it can lead to the formation of mountain systems. In the case of the collision of two continental plates, a high mountain range is formed, as happened with the Himalayas, which were created from the collision of the Indian and Eurasian plates around 50 million years ago. The process of plate drift also causes earthquakes and volcanic activity. When plates move, tension accumulates at their boundaries, which is eventually released in the form of earthquakes. One of the most famous examples is the San Andreas Fault in California, where the Pacific Plate collides with the North American Plate, creating tension that leads to frequent earthquakes. Mid-ocean ridges, such as the Mid-Atlantic Ridge, are places where plates diverge, and magma rises to the surface, forming new crust. This process, known as spreading, has been occurring for the last 100 million years and leads to the expansion of the ocean floor. Every few million years, plate tectonics changes the face of the Earth. For example, more than 300 million years ago, all continents were united into the supercontinent Pangaea, which began to break apart into the present-day continents around 200 million years ago. This process continues today. In millions of years, continents may once again join to form a supercontinent. Scientific models suggest that in a few hundred million years, all continents may reunite. Thus, plate tectonics not only creates the current landscape, but also lays the foundation for future changes, making Earth a dynamic and evolving planet. Plate tectonics is not just the movement of the crust. It is a complex process involving various geological forces that influence climate, ecosystems, and even human history. For example, volcanic eruptions caused by plate movement can affect climate by releasing large amounts of volcanic ash and gas into the atmosphere, leading to a decrease in Earth's temperature. The Toba volcano in Indonesia, which erupted around 74,000 years ago, caused global climate changes that could have influenced human evolution. These processes have been occurring for billions of years, and Earth science actively studies them, using radiometric dating methods to determine the age of formations and reconstruct the history of plate movement. Scientific research shows that, despite the slow pace, plate tectonics is one of the most powerful forces shaping our planet, Every few million years, these slow but inexorable movements create new landscapes, forming oceans, mountains, and plains. The complex nature of tectonic processes not only makes Earth unique, but also contributes to why life on our planet continues to evolve and adapt. Subduction is a process in which one tectonic plate slowly descends under another, returning to the Earth's mantle. This phenomenon occurs in subduction zones where oceanic and continental plates collide. For example, in the region of the Pacific Ring of Fire, where the Nazca Plate is subducting under the South American Plate, a well-defined subduction process is observed. The rates of subduction can vary from several millimeters to several centimeters per year. Between the plates, tension builds up over decades and even centuries. This tension is caused by friction between the plates, as one plate attempts to pass under another, but cannot do so easily due to resistance. As a result of this friction, energy accumulates, which eventually leads to sudden shifts that cause earthquakes. For instance, the earthquake in Chile in 2010 occurred due to the release of accumulated tension between the plates and had a magnitude of 9, making it one of the strongest earthquakes in history. This process also contributes to the formation of volcanoes as the subducting plate begins to melt, creating magma that rises to the surface. Volcanic activity in subduction zones can be highly destructive. For example, the eruption of the Cotopaxi volcano in Ecuador, located in a subduction zone, caused significant damage and threatened nearby settlements. Subduction also influences the formation of mountain ranges, such as the Andes, which have arisen from multi-generational processes of tectonic shifts. Tension in subduction zones does not disappear instantly. It accumulates, and once a critical point is reached, there is a sudden movement of the plates that can cause not only earthquakes, but also tsunamis, as was the case in the Indian Ocean in 2004. Therefore, the process of subduction is one of the key factors shaping the landscape of the Earth and affecting the lives of people and ecosystems in these regions. In subduction zones, not only physical effects occur, but also changes in ecosystems, as earthquakes and volcanic eruptions can lead to changes in climate and ecology over vast areas. In the process of seafloor spreading, magma rises from the depths of the Earth through faults in the oceanic crust, creating new crust. This process begins at mid-ocean ridges, such as the East Pacific Rise, which stretches over 6,000 kilometers from the Arctic to the Antarctic. In these zones, temperatures reach thousands of degrees Celsius, and pressure exceeds hundreds of atmospheres. When magma reaches the surface, it quickly cools and solidifies, forming new oceanic crust primarily composed of basalt. For example, in the 1960s, during the mission Gloucester, researchers found that the rate of seafloor spreading in the East Pacific Rise area is about 5 centimeters per year. Although this speed may seem insignificant, over millions of years it leads to significant changes in the positions of continents. Seafloor spreading is also accompanied by submarine volcanism, which occurs in complete darkness at depths of several kilometers underwater. Volcanic islands like Hawaii were formed as a result of this process. Hawaii is located on the Pacific Plate, which moves over a hotspot, causing eruptions and the formation of new volcanoes. These eruptions can continue for millions of years, eventually creating vast islands. In 1984, one of the most famous eruptions on Hawaii occurred when the volcano Kilauea began spewing lava, leading to the formation of new land and changes in the island's landscape. Each new volcanic eruption adds to the oceanic crust, gradually expanding continents and altering the shape of oceans. During seafloor spreading, rifts are also formed, which are cracks that appear on the surface as plates move apart. For example, in the Hudson Bay Rift, active seafloor spreading processes were first described in the 1970s. These rifts are unique ecosystems where specialized organisms like tube worms and bacteria live, feeding on substances released from underwater sources. Scientific research shows that seafloor spreading not only creates new crust, but also influences the Earth's climate. Each time magma is expelled onto the surface, gases such as carbon dioxide and water vapor are also released, which can affect the composition of the atmosphere. Volcanic eruptions on the ocean floor can lead to changes in temperature regimes and even changes in ocean currents. For example, in the 1830s, a volcanic eruption in the Indian Ocean altered currents in that region, affecting the climate in eastern Africa. Therefore, the process of seafloor spreading is one of the key mechanisms that shape our planet. It not only creates new crust, but also changes ecosystems, influences climate, and even contributes to the formation of new islands. Seafloor spreading has been occurring for millions of years and continues to change the world we live in. There is evidence that in the future, this process may lead to the creation of new continents as plates continue to diverge and collide. As a result, we can observe continents slowly moving apart, making Earth dynamic and constantly changing. Scientific research continues, and each new discovery reveals more mysteries about the formation and development of our planet. Volcanic activity in the oceans remains an important area of study, as it can provide insights into the processes occurring deep within the Earth. Supercontinents represent vast landmasses that form through the combination of separate continents into a single entity and subsequent disintegration. This process, known as the supercontinental cycle, occurs over geological timescales, spanning millions of years. On average, supercontinents form and break apart approximately every 300 million years. When continents unite, they create extensive ecosystems where species can freely migrate and interact, leading to an increase in biological diversity. However, over time, as continents begin to disperse, periods of isolation occur. These isolations can last tens of millions of years, creating unique conditions for evolution, allowing species to adapt to new environments and, in some cases, leading to the formation of new species. The process of combining and breaking apart supercontinents also significantly influences Earth's climate. When landmass gathers in one place, it alters atmospheric and oceanic currents, creating new climatic zones. For example, the presence of a large supercontinent can lead to the formation of arid conditions in its central part, resulting in reduced rainfall. Meanwhile, on the periphery of the supercontinent, more humid conditions can arise, leading to the formation of tropical forests and other ecosystems. Supercontinents affect oceanic currents, changing their direction and strength. For instance, when landmass separates, it can lead to the formation of new seas and oceans, creating new pathways for ocean currents. These changes, in turn, can influence the global climate system, altering temperatures and rainfall levels in different parts of the planet. Additionally, supercontinents play a crucial role in Earth's geological activity. In areas where continents collide, mountain ranges, such as the Himalayas, and volcanic activity can arise. This not only impacts geography, but also creates new ecosystems, as various plant and animal species adapt to new conditions, forming unique biomes. The study of supercontinents allows researchers to examine not only surface changes on Earth, but also internal processes, such as plate tectonics. For example, when plates collide, it can lead to the formation of folds and faults, which, in turn, influence the distribution of resources such as oil and minerals. These resources often concentrate in areas of past geological activity, making an understanding of the supercontinental cycle important for contemporary research in geology and ecology. Supercontinents also serve as key objects of study in biogeography. During periods when land was united, species could freely migrate between regions, facilitating the exchange of genetic information and species diversity. When the Earth's crust breaks apart, isolation leads to the creation of unique ecosystems with their characteristic species. Scientific research, such as paleontological work, shows that many species that coexisted at one time could develop in parallel, but diverged in their evolutionary paths due to isolation. Arguments supporting the cyclical nature of supercontinents are becoming increasingly well-founded due to modern geological data and plate tectonic analysis. For example, scientists like Dr. Richard Hawkins and his team have discovered that continental movement is linked to convective flows in Earth's mantle. These flows can alter the speed and direction of plate movement, influencing the periodicity of supercontinent formation and disintegration. Understanding these processes can help predict future changes on our planet, such as potential continental collisions and the formation of new supercontinents in the future. Scientific understanding of supercontinents continues to evolve, with each new discovery adding details to this complex picture. For instance, recent research suggests that some continents may already be moving towards a new union, which could occur in several tens of millions of years. These findings confirm that Earth, like oceanic currents, is a dynamic system constantly changing under the influence of various geological and climatic factors. Supercontinent Pangaea existed approximately from 300 million to 230 million years ago, during the Paleozoic and Mesozoic eras. Its shape resembled a vast bubble, elongated from north to south, with one side facing the equator. Pangaea occupied about half of the Earth's landmass and included the territories of modern-day North and South America, Africa, Europe, Asia, and even Australia. The center of Pangaea was arid, creating desert conditions and extensive plateaus, such as the Transvaal in South Africa. The interior regions of the continent experienced severe water scarcity, leading to the formation of vast deserts where temperature fluctuations could reach critical values, ranging from 30 to 100 degrees Celsius within a day. In contrast, the coastal areas were characterized by monsoon climates, where seasonal rains brought life and diversity. For instance, the southeastern coast of Pangaea was home to powerful monsoons over oceanic waters, bringing abundant rainfall and allowing the development of tropical forests. However, on most of the landmass, a temperate climate was absent, which affected the biosphere and ecosystems. As a result, the animal and plant life of Pangaea was unique. It included primitive reptiles like the Deinocheirus and primitive mammals, creating a unique ecosystem without the familiar climate zones we know today. Research shows that the conditions of Pangaea were responsible for significant changes in the evolution of life. Many species went extinct, while new ones adapted to the specific conditions and began to occupy vacant niches. Geologists and paleontologists, such as Dr. Edward Kearns from Cambridge University, note that the climatic conditions of this continent played a key role in shaping modern ecosystems and the distribution of species on Earth. Considering that Pangaea existed during a time when the level of carbon dioxide in the atmosphere was significantly higher than today, its climate can be seen as a precursor to modern climate changes, opening new horizons for studying the influence of geology on climate change. The study of the Pangaean ecosystem remains relevant, as it may provide insights into future changes on our planet. One remarkable fact is that Pangaea began to break apart around 200 million years ago due to tectonic processes, leading to the formation of the modern continents and oceans. The breakup of Pangaea is not just a historical fact, but a colossal geological process that spanned more than 100 million years. It began around 200 million years ago, when a single continent began to slowly tear apart under the influence of tectonic forces. During this time, in the Triassic period, the continent was surrounded by one vast ocean, which scientists call panthalassa. The first signs of the breakup appeared as cracks that gradually deepened into the Earth's crust. Around 190 million years ago, the first narrow sea appeared, separating the northern part of Pangaea, called Laurasia, from the southern part, Gondwana. This process occurred very slowly, at a rate of about 5 centimeters per year, allowing the continents not only to drift apart, but also to form new geological structures. Gradually, over the next millions of years, the cracks widened, forming straits and bays that later became wide oceans. Around 180 million years ago, the process of opening the Atlantic Ocean began, when vast water spaces formed between Laurasia and Gondwana. As a result of this breakup, the ancient continent gave rise to the modern continents: North America, South America, Europe, Asia, Africa, Australia, and Antarctica. Around 100 million years ago, during the Cretaceous period, the new oceans reached their full development, dividing the continents into the distances we observe today. Scientists also note that this process was not uniform. Some land areas were submerged underwater, while others rose, creating new mountain ranges. As a result of tectonic activity, famous mountain ranges such as the Appalachians and the Andes began to form due to the collision of tectonic plates. This was a time when significant changes in climate and ecosystems occurred on the planet. leading to the appearance of new flora and fauna. Around 65 million years ago, at the end of the Cretaceous period, the breakup of Pangaea was completed, finally dividing the Earth's landmass into the modern continents and opening new horizons for geological and ecological research. During the breakup of Pangaea, not only oceans but also new ecosystems were formed, which became the basis for further evolution of life on Earth. The formation of the Atlantic Ocean began approximately 100 million years ago, when the process of continental separation began due to tectonic movements. At this stage, a narrow strait between Africa and America gradually widened, initially forming a small oceanic basin that eventually evolved into the modern Atlantic Ocean. One of the key events in this process was the movement of continental plates, which led to the formation of rifts on the ocean floor. As a result, around 70 million years ago, there was a significant increase in ocean floor area, which contributed to the formation of new ocean currents. These currents, such as the Gulf Stream, began to influence the climate of adjacent continents, thereby altering ecosystems both in the ocean and on land. For example, the warm waters of the Gulf Stream, flowing from the equator to the north, contributed to a milder climate on the eastern coast of North America and in Western Europe. This led to the development of unique ecosystems that could not exist without these warm currents. Simultaneously with the expansion of the ocean, significant changes occurred in the composition of marine life in its waters. The appearance of new maritime routes created conditions for the migration of various species, which became a catalyst for evolutionary processes. For example, around 60 million years ago, when the ocean had reached its modern size, there was a mass spread of marine mammals such as dolphins and whales. These animals began to adapt to new conditions, which was possible due to the diversity of ecosystems created by the new marine currents. The opening of new routes also led to more active exchange of species between different regions, which contributed to an increase in biological diversity. Scientific research conducted in the last few decades shows that the increase in the area of the Atlantic Ocean also contributed to changes in global climate, influencing the distribution of precipitation and temperature in various parts of the world. For example, the increased temperature of the ocean water causes more intense tropical storms, which have serious consequences for ecosystems and human activities. These changes continue to this day, emphasizing the importance of the Atlantic Ocean as a key element of the Earth's climate system. As the ocean continues to expand, its influence on climate and ecosystems will only increase, making it a subject of constant study for scientists around the world. Volcanism is a powerful process that demonstrates how the internal energy of the Earth finds an outlet through cracks in the crust, expelling molten rocks, known as magma, to the surface. Within the planet, temperatures can reach several thousand degrees Celsius, and this hot magma strives to escape to the surface. The process of volcanism begins in the mantle, where thermodynamical reactions cause some rocks to melt. For example, in the Earth's mantle, there are materials containing iron and magnesium that become liquid at high temperatures. These molten rocks quickly rise upward, colliding with the solid crust, which acts as a kind of shield. However, this crust is not impervious. It contains cracks and faults that can allow magma to reach the surface, turning into lava. Depending on the pressure that accumulates in the magma chambers, various types of eruptions can occur, from the quiet flow of lava to powerful explosions. During a volcanic eruption, not only is magma expelled, but also various gases such as water vapor, carbon dioxide, and sulfur dioxide, which can form dangerous clouds. These gases, contained in the magma, can cause explosive eruptions when pressure drops rapidly, as observed in volcanoes with viscous magma. These explosions can eject a large amount of ash and debris into the atmosphere, significantly affecting the climate. Volcanism plays a key role in the formation of the Earth's crust, creating new lands and altering landscapes. For example, islands formed by volcanic activity can emerge from the depths of the ocean in just a few centuries. The most famous examples of such islands are the Hawaiian Islands, which were formed from multiple underwater volcanic eruptions. Research shows that volcanic activity can significantly impact ecosystems, both in the short and long term. Volcanism also has serious consequences for the climate. For instance, Large eruptions can release enough sulfur into the stratosphere to form aerosols that reflect sunlight and temporarily cool the planet. The internal forces of the Earth are continually held back by the crust, but the tension resulting from these forces is constantly increasing. This creates an atmosphere of expectation, where any movement in the planet's interior could lead to catastrophic consequences. Volcanism thus becomes a symbol of this struggle between internal forces and external constraints, constantly reminding us of the dynamic nature of our planet. Research shows that over the past 10,000 years, there have been more than 80 major volcanic eruptions that have not only changed the landscape, but also the life on Earth. Trap volcanic activity is a unique phenomenon that manifests as large-scale lava flows capable of covering vast territories. These eruptions occur due to tectonic processes, where molten rock or magma rises to the surface through cracks in the Earth's crust. The most famous traps are found in places like the Deccan Plateau in India, where lava layers can reach thicknesses of up to 2 kilometers and extend over hundreds of thousands of square kilometers. Lava flows slowly across the surface, forming wide, flat plateaus. Unlike conical volcanoes, traps create not elevations, but extensive plains that alter the landscape over thousands of square kilometers. This happens because lava flows can overlap, forming multi-layered structures. For instance, in the Deccan Plateau region, more than 100 lava layers have been identified, each with its unique chemical and mineralogical composition. Research shows that over a period from about 60 million years ago to 50 million years ago, approximately 100 eruptions occurred, each capable of releasing tens of cubic kilometers of magma into the atmosphere. Thus, trap volcanic activity not only leaves geological formations, but also significant changes in climate and biosphere. During eruptions, such volcanoes can release large amounts of carbon dioxide and sulfur dioxide into the atmosphere, leading to the greenhouse effect and acid rain. These processes contributed to mass extinctions of species, as seen around 60 million years ago, when the eruptions of the Deccan traps may have been one of the factors contributing to the extinction of dinosaurs. Scientific research conducted in the 2000s showed that the Deccan lava flows contain organic carbon traces, indicating the influence of these volcanoes on the environment. Plateaus formed by such eruptions often have a stepped structure, as lava flows gradually cool and solidify, forming sharp cliffs and terraces. This creates unique ecosystems where flora and fauna adapt to different conditions at each level. For example, in places like the Columbia Plateau in the USA, trap volcanic activity has created extensive fields of basaltic roads where rare plant species that can survive in poor soils grow. Trap formations are not only fascinating geological objects, but also important indicators of the climate changes that have occurred on Earth over millions of years. As a result of such massive eruptions, as in the Deccan, unique landscapes and complex ecosystems have been formed, which continue to be studied by scientists. Each layer of lava solidified on the surface represents a page in the geological history of the planet, preserving secrets about Earth's past and its evolution. Siberian traps are among the most extensive volcanic formations on the planet, having formed at the end of the Cretaceous period, approximately 130 million years ago. These colossal layers of basaltic lava, covering an area of more than 1 million square kilometers, were the result of a series of powerful volcanic eruptions that occurred over several million years. The volcanic activity was so intense that the gases and ash expelled into the atmosphere formed clouds that obscured the sky and significantly reduced the amount of sunlight reaching the Earth's surface. This process led to what is known as the volcanic winter, during which the planet's temperature dropped, having a catastrophic impact on ecosystems. Research indicates that over several decades, the climate conditions changed so drastically that the level of carbon dioxide in the atmosphere reached critical values, contributing to global warming after the end of this icy period. A prime example of this is how temperature and atmospheric composition changes could influence species migration and ecosystem distribution. Scientists believe that such changes could have been one of the factors contributing to the mass extinction of dinosaurs. Volcanic emissions contained large volumes of sulfur, which contributed to the formation of aerosols that reflected sunlight, further lowering the temperature. Climate change models show that such conditions could have persisted for up to 100,000 years, leading to long-term changes in the biosphere. These phenomena also preceded the formation of vast coal and oil deposits, which later became important resources for humanity. Siberian traps are not only geological formations, but also a significant indicator of how volcanic activity can influence climate and ecosystems on a global scale. The unfortunate consequences of these eruptions remain a subject of active research. For instance, in 2018, a group of Russian scientists led by Professor Alexei Sidorov published results showing that analysis of carbon isotopes in the rocks of the traps indicates significant changes in ecosystems due to volcanic activity. These data confirm that active volcanic processes not only shape the landscape, but also have a profound impact on the biosphere. Siberian traps continue to be a subject of scientific research, which will help better understand how volcanic activity can influence future climate changes. Siberian traps are linked to the Permian extinction event that occurred around 250 million years ago, which wiped out nearly 95% of all marine life and 67% of terrestrial species. Volcanic activity caused by the formation of these traps led to catastrophic changes in the atmosphere and oceans. The main culprit behind this mass extinction was volcanic gas, particularly carbon dioxide, which quickly accumulated in the atmosphere. Carbon dioxide, released from the heated interior of the Earth, altered the chemical composition of the atmosphere, leading to global warming. This, in turn, caused a rapid acidification of the oceans as part of the carbon dioxide dissolved in water, forming carbonic acid. According to calculations by scientists, the pH of the oceans dropped to critical levels, which had a fatal impact on marine organisms such as corals and mollusks, which could not adapt to such rapidly changing conditions. Volcanic activity also led to the formation of aerosols, which blocked sunlight and caused sharp temperature fluctuations. As a result of these processes, the Earth's climate became unstable, from rapid cooling to constant temperature changes, which further complicated the conditions for survival. Research shows that during this period, oceanic ecosystems experienced catastrophic stress, leading to mass mortality of organisms. As a result of these changes, Earth's ecosystems were on the brink of complete destruction, and only a few species survived, which became the basis for future evolution. Scientists such as David Irk and his team, studying samples of sedimentary rocks from that time, concluded that volcanic emissions were the main cause of climate and ecosystem changes that survived the extinction. Volcanic activity continued for several million years, and during this time, numerous eruptions occurred, each adding new volumes of carbon dioxide and other gases to the atmosphere. According to estimates, the total amount of carbon dioxide released into the atmosphere as a result of these processes was around 30 billion tons, which exceeded all previous emissions over millions of years. These data provide insight into the scale of the tragedy that occurred on the planet during the period when volcanic activity created conditions that became catastrophic for life on Earth. Throughout the history of Earth, there have been mass extinctions that have left a profound mark on the planet's biosphere. These events are characterized by the simultaneous disappearance of numerous species of living organisms, leading to significant changes in ecosystems. Mass extinctions often occur as a result of catastrophic changes in the environment, such as volcanic activity, climate change, or meteorite impacts. One of the most well-known examples is the extinction event that occurred around 66 million years ago, when a meteorite with a diameter of about 10 kilometers struck Earth, causing the mass extinction of dinosaurs and many other species. As a result of this event, approximately 75% of all species that inhabited the planet at that time became extinct. In such moments, life on Earth becomes vulnerable, and ecosystems that have evolved over millions of years can be destroyed in a matter of moments. Mass extinctions are always accompanied by a sharp change in biological diversity. For example, at the end of the Permian period, around 250 million years ago, the most extensive extinction event in Earth's history occurred, when more than 95% of marine and 75% of terrestrial species disappeared. This event is known as the Great Dying, and its causes are still debated among scientists. Some researchers attribute it to volcanic activity in the region of modern-day Siberia, where vast cracks formed, releasing carbon dioxide and other gases into the atmosphere, leading to a rapid change in climate. Other factors, such as changes in sea level and oxygen content in the atmosphere, may also have played a role. These processes demonstrate how easily the biosphere can be disrupted by global changes. Scientists continue to study these events to understand how they influence the development of life on Earth and what lessons we can learn from them for today. Each time a mass extinction occurs, life on the planet begins anew, opening up new evolutionary paths. Contemporary research by scientists such as Dr. Elizabeth Colbert, author of The Sixth Extinction, highlights that we are on the brink of a new mass extinction caused by human activity. According to estimates, current rates of species extinction are 100 to 1,000 times higher than the natural rates that existed before the appearance of Homo sapiens. This puts not only individual species but entire ecosystems that support life on Earth at risk. It is important to note that species extinction not only affects the visible manifestations of life, but also deeply influences genetic diversity, which is the basis for adaptation and survival. Each mass extinction leaves behind voids in ecosystems that are filled by new forms of life. But this process takes millions of years. Today, there are many organizations working to preserve biodiversity and prevent further extinctions. For example, the World Wildlife Fund identifies the main threats to species: habitat destruction, climate change, and environmental pollution. Scientific research shows that protective measures such as creating nature reserves and protecting endangered species can help preserve unique ecosystems. At the same time, to successfully combat these threats, it is necessary to understand the processes that led to previous extinctions to avoid repeating past mistakes. Each species that disappears from the face of the Earth affects the entire web of life, highlighting the fragility of our existence in the face of global changes. Over the past 100 years, around 14,000 animal and plant species have been officially recognized as extinct, and this is just the tip of the iceberg. Scientific data indicate that without active actions to protect the environment, we may witness another catastrophe that will change the face of the planet. The Permian extinction, which occurred around 250 million years ago, was the most catastrophic in Earth's history, wiping out up to 96% of all marine species and around 70% of terrestrial ones. Known as the Great Dying, this event shook the planet's ecosystems, destroying numerous groups of organisms. At this time, life in the oceans was slowly disappearing due to factors such as climate change, volcanic activity, and a decrease in oxygen levels in the water. For instance, in the region of modern-day Ural Mountains, there was intense volcanic activity, which led to the release of vast amounts of carbon dioxide and sulfur, resulting in acidification of the oceans. This phenomenon caused the catastrophic extinction of fauna, including marine animals like trilobites and brachiopods, which could not adapt to the drastically changed conditions. On land, the extinction affected many plant and animal species, including ancient reptiles and amphibians. Studies show that forests, once teeming with life, became desolate, and ecosystems lost their diversity. For example, fossil remains indicate that the diversity of species in these ecosystems sharply declined, leading to the formation of desert landscapes where once there were rich ecosystems. During this time, entire groups of organisms, such as giant ammonites and some types of corals, disappeared, unable to survive in conditions where water temperature significantly increased. Scientific data suggests that these changes did not occur instantaneously, but took millions of years, creating conditions for the slow decline of life. Ultimately, the Permian extinction marked the beginning of a new era in Earth's history, known as the Mesozoic era, during which dinosaurs and other reptiles began to dominate. Research shows that after this event, life on the planet recovered, but in different forms, demonstrating that ecosystems can regenerate, although the path to recovery requires time and changes in the conditions of existence. After the Permian extinction, Earth entered a period of unprecedented change. Ecosystems that were once teeming with diverse forms of life became desolate, leaving only a few survivors. These surviving organisms became dominant in the new conditions, which had changed dramatically. For instance, Around 95% of all marine species and more than 70% of terrestrial animals disappeared, simplifying food chains. In their place, new, less diverse ecosystems emerged, where groups like crocodile-like reptiles and primitive mammals began to dominate. Instead of the abundance of species that thrived before this catastrophic event, ecosystems became more uniform, and new ecological niches appeared that needed to be filled. These niches did not remain empty for long. Evolution, as it were, rebooted, beginning to create new life forms adapted to the changed conditions. For example, the first dinosaurs, which appeared around 230 million years ago, exhibited remarkable diversity in form and size, from small two-legged predators to giant herbivores like the Brachiosaurus, which reached heights of up to 25 meters. Climate change also played a role. The planet's temperature rose, creating warm and humid conditions ideal for plant growth. At this time, coniferous forests like Araucarias began to develop, becoming the primary food source for new animal species. This interaction between plants and animals led to the formation of new ecosystems, allowing many creatures to adapt to the new reality. On land, the first mammals, such as small, mouse-like creatures, began to appear, surviving in conditions where most large forms of life had perished. These mammals began to occupy ecological niches that had been vacated after the mass extinction. Their ability to live nocturnally and maintain a high metabolism allowed them to survive in the changed conditions. In the oceans, significant changes were also observed. Simple organisms like plankton began to repopulate their niches, contributing to the restoration of marine ecosystems. At this time, new mollusk and coral species appeared, forming the basis for future reefs. An example is the appearance of the first brachiopods, which dominated marine ecosystems due to their ability to filter water. Different groups of animals began to occupy new ecological niches, leading to the emergence of entire new ecosystems. This process of creation and filling of new niches became the basis for further diversification of life, which reached its peak during the Mesozoic era. As a result, the planet began to gradually recover from the aftermath of the Permian extinction, and within a few million years, new life forms began to dominate in various parts of the world. It is important to note that this process created conditions for the emergence of future life forms, such as dinosaurs, which became symbols of the Mesozoic era. Cosmic collisions, or impact events, represent some of the most destructive processes ever to have occurred on Earth. These events occur when large celestial bodies, such as asteroids or comets, collide with the planet's surface, instantly altering its conditions. As a result, catastrophic changes in climate, geology, and ecosystems take place. For instance, the energy released during a collision can be equivalent to millions of atomic bombs, leading not only to local destruction, but also to global consequences. The shock wave, spreading out, creates powerful earthquakes, raises vast amounts of dust and debris into the atmosphere, which blocks sunlight and causes rapid cooling on the planet. This phenomenon is known as the impact winter and can last for months or even years, significantly impacting photosynthesis and life on Earth. Research shows that such events can cause mass extinctions of species, as seen at the end of the Cretaceous period, when a collision with a large object led to the extinction of dinosaurs. Even small asteroids, just a few kilometers in diameter, can create conditions that threaten life on Earth. For example, a collision of this size can release enough energy to ignite forests over large areas and create acid rain, leading to the destruction of ecosystems. The fragility of planetary equilibrium becomes particularly evident when we consider that Earth is constantly subjected to the influence of celestial bodies. Astronomers estimate that around 30 tons of cosmic material falls on our planet each year. Although most of these objects burn up in the atmosphere, some reach the surface, and their impact can be significant. Collisions with objects several dozen meters in size can cause city-level destruction, while larger bodies can lead to planetary-scale climate change. This unpredictability makes Earth vulnerable to cosmic forces, and each new object approaching the planet could herald a new catastrophe. Scientific research continues, and astronomers actively monitor potentially hazardous objects to predict their trajectories and minimize risks. It's important to note that even small changes in the orbits of such objects can have catastrophic consequences. For example, in the 12th century, Chinese astronomers recorded the fall of meteors that led to significant changes in weather conditions. Impact events remind us that life on Earth depends on a delicate balance that can be disrupted at any moment by a cosmic catastrophe. Their impact on the planet and life on it remains the subject of numerous studies and discussions. The emergence of new technologies, such as the observation of near-Earth objects and the development of protection methods, opens up new possibilities for understanding and preventing the consequences of such catastrophes. When a celestial body, such as a meteorite or asteroid, enters Earth's atmosphere, it collides with air at incredible speeds, often exceeding 10 kilometers per second. This results in rapid heating due to friction, causing the temperature on its surface to reach thousands of degrees. In most cases, the meteorite burns up in the atmosphere, leaving a bright trail in the sky, but if it is large enough, it reaches the Earth's surface. Upon impact with the Earth's crust, a colossal amount of energy is released, equivalent to the explosion of several thousand tons of TNT. This energy creates a shock wave that spreads through the atmosphere, causing damage over a significant distance from the impact site. For example, the meteorite that struck Chelyabinsk in 2013 had a power of about 14 kilotons, resulting in damage to over 700 buildings and injuring more than 1,500 people. Upon impact, molten material is ejected into the air, rising to heights of several kilometers and forming clouds of ash and debris. This forms an impact crater, which can vary in size and shape depending on the mass and speed of the celestial body. The crater typically has a characteristic central elevation formed by material ejected during the impact, which flows towards the center after the impact. Seismic waves generated by the impact spread across the planet, causing earthquakes that can be detected at significant distances from the impact site. For instance, the Chicxulub crater in Mexico, formed approximately 65 million years ago, was created by a meteorite estimated to be about 10 kilometers in diameter. Its powerful impact caused global climate changes, which may have been the cause of the mass extinction of dinosaurs. Recently, in 2018, scientists discovered a crater formed by a meteorite in the region of Kursk, which confirms that such events continue to occur today. The Chicxulub crater, located on the Yucatan Peninsula in Mexico, has a diameter of approximately 130 kilometers and formed around 65 million years ago. This crater is one of the most significant geological formations on Earth, as its formation is linked to a catastrophic event, the impact of a giant meteorite, estimated to have had a diameter of around 10 kilometers. The impact was so powerful that its effects were felt worldwide, causing massive fires, tsunamis, and rapid climate change. The crater itself is hidden beneath layers of sedimentary rocks, but its structure includes a central peak that rises several kilometers and is composed of ejected materials. Scientists from various countries, including a team led by Dr. Alan Hill from the University of Pennsylvania, study the geological layers around the crater to understand the consequences of this event. This site has become a crucial object of study because it contains evidence of how extraterrestrial bodies can influence the evolution of life on our planet. The complex processes resulting from the impact led to the extinction of around 70% of all life forms, including dinosaurs, opening new horizons for understanding biological adaptation and evolution. The place where this collision occurred resembles a giant bowl surrounded by tropical forests and wild nature, contrasting with its catastrophic history. The study of the crater continues using modern methods such as radar sounding and analysis of rock samples, allowing scientists to gather new data on the timing and circumstances of the impact. These studies confirm that the Chicxulub crater is not just a geological anomaly, but a testament to how the cosmos has intervened in the history of Earth. On its floor, scientists find fossilized remains and remnants of ancient organisms that witnessed this catastrophic event. For example, in 2018, a team of Mexican and American geologists discovered fossilized marine organisms that lived in oceans before the impact. The Chicxulub crater serves not only as an object of study, but also as a reminder of the fragility of life on our planet. An asteroid that created the Chicxulub crater had a diameter of about 10 kilometers and was moving at a speed of approximately 26 kilometers per second. This collision occurred around 66 million years ago and had catastrophic consequences. The energy released in the impact was equivalent to billions of atomic bombs dropped on Hiroshima, leading to the instantaneous vaporization of vast volumes of rock and the formation of a crater with a diameter of about 130 kilometers. At the moment of impact, a flash of light brighter than sunlight was produced, visible from hundreds of kilometers away. The light was so intense that it could have blinded all living organisms within a radius of many tens of kilometers. The shockwave from the collision caused earthquakes and tsunamis that destroyed ecosystems and wiped out all life in the region. Materials ejected into the atmosphere polluted the sky, creating clouds of dust and aerosols that blocked sunlight and led to a sharp drop in global temperature. This phenomenon, known as nuclear winter, lasted for months, if not years, causing mass extinctions. Studies show that up to 70% of all species on Earth disappeared as a result of this cataclysm. Some scientists, such as Dr. Alan Alvarez from the University of California, claim that this event played a key role in the transition of epochs, paving the way for mammals and, ultimately, the emergence of humans. After the collision, the Chicxulub crater became not only a geological anomaly, but also a significant object for understanding the processes of extinction and evolution. As a result of the impact, tons of debris were ejected into the atmosphere, reaching Earth's orbit and causing meteor showers for many years after the catastrophe. This collision altered the climate, ecosystems, and ultimately, the history of all life on the planet. The impact of the Chicxulub meteorite triggered a series of catastrophic events that transformed the planet's appearance in just a few hours. The first consequences were the firestorm that engulfed an area with a radius of several hundred kilometers. Temperatures in the impact zone reached thousands of degrees Celsius, causing immediate combustion of vegetation, wood, and even animals. Hundreds of square kilometers of forests burned in minutes, turning them into ash and charcoal, while clouds of smoke rose into the atmosphere, creating a dark veil that blocked out the sun. These conditions set the stage for further destruction of ecosystems that had existed on Earth for millions of years. Simultaneously, a powerful earthquake was registered worldwide. The seismic waves reached a magnitude of 9 on the Richter scale, leading to the destruction of both natural formations and human settlements, if they existed at the time. Additionally, the impact caused massive tsunamis, with heights exceeding 100 meters. These waves swept across the coastlines, destroying everything in their path, including cliffs, trees, and animals. Underwater, the seabed rose and fell, forming new underwater landscapes. Furthermore, the shockwave sent a massive amount of water into the air, which later fell back to Earth as acidic rain. These rains had a pH level below 3, making them highly toxic to all forms of life. Stable ecosystems that had evolved over millions of years were on the brink of collapse. Plants, unaccustomed to such acidity, began to die, and animals dependent on them faced food shortages. This day marked the beginning of the end for many species, as their habitats were destroyed by the catastrophic events. Studies by scientists indicate that as a result of these events, approximately 75% of all species on the planet went extinct. The consequences of the Chicxulub impact were not just local catastrophes, but a global tragedy that altered the entire course of evolution. The world, plunged into darkness after the Chicxulub impact, experienced catastrophic changes known as the impact winter. The release of a massive amount of dust and aerosols into the atmosphere made sunlight almost inaccessible. Studies show that this process took from several months to several years, during which the surface temperature of the planet dropped by 10 to 20 degrees Celsius. This led to a sharp reduction in photosynthesis. Plants that depended on sunlight for producing oxygen and creating food began to die. For example, in large ecosystems such as tropical forests, there was a mass extinction of tree plants, which in turn disrupted familiar food chains. As a result, herbivorous animals like dinosaurs, and then all predators that depended on them, suffered. This led to the survival of only the most adaptable species, such as small mammals and some reptiles. Research conducted in the 90s of the 20th century shows that these conditions were responsible for the extinction of about 75% of all species on the planet, including not only dinosaurs, but also many marine creatures. The impact winter lasted approximately 1 to 2 years, but the long-term consequences were catastrophic. Scientists like Professor David Polly from the University of Leicester claim that the climatic changes caused by the impact led to a change in the usual distribution of ecosystems, and the restoration of nature took millions of years. The vegetation that survived adapted to the new conditions, and eventually, new ecosystems began to form on the planet. However, these changes did not happen instantaneously. For several decades after the impact, Earth was desolate, and only after several million years after the catastrophe did the recovery processes begin. Around 70 million years later, during the Paleogene epoch, the world was once again filled with diverse forms of life, but completely different from those that existed before the impact. Research conducted in recent decades shows that the impact winter and the associated changes in ecosystems were catalysts for the evolution of mammals, which then dominated the planet. Scientific data confirm that this extinction paved the way for the appearance of modern species, including humans. The Chicxulub impact, which occurred approximately 66 million years ago, was a catastrophic event that forever altered the face of Earth and led to the extinction of the dinosaurs. This powerful impact, caused by the collision of an asteroid about 10 kilometers in diameter with the territory of modern-day Mexico, brought about massive changes in the planet's climate and ecosystems. Research by scientists shows that the shockwave generated by the collision destroyed flora and fauna within a radius of hundreds of kilometers, and the ejection of dust and gas into the atmosphere led to a sharp decrease in sunlight. This resulted in what is known as the impact winter, which lasted from several months to several years. It is known that the temperature on the Earth's surface fell by several dozen degrees, creating conditions in which the dinosaurs, which had dominated the planet for more than 150 million years, found themselves in a hopeless situation. Despite their majesty and adaptive capabilities, different groups of dinosaurs were unable to survive such abrupt changes. For example, herbivorous dinosaurs such as Triceratops and Brachiosaurus became victims of food scarcity, as their usual food sources, such as large coniferous forests, went extinct. Predators like Tyrannosaurus rex lost access to their prey and found themselves in conditions where there was no food. Paleontologists find evidence of this massive extinction in the form of fossils that show a sharp reduction in the diversity of species in the layers formed after the impact. For example, at the end of the Cretaceous period, when there were more than 70 different species of dinosaurs, their number had decreased to less than 20 by the beginning of the Paleogene. This catastrophe cleared the ecosystem of the dominance of dinosaurs and created conditions for the flourishing of mammals, which began to occupy the niches left by the extinct giants. The Chicxulub impact was not just the end of the era of dinosaurs, but also the beginning of a new epoch, when completely different forms of life began to dominate the planet. Meanwhile, small mammals that had previously been secondary creatures began to evolve, occupying ecological niches that had been vacated by the disappearance of dinosaurs. Scientific research shows that this event was the catalyst for the emergence of modern mammals and ultimately humans. Today, approximately 85% of all species on Earth have gone extinct as a result of this impact. Small mammals, including the ancestors of modern rodents and insectivores, became the primary survivors after the catastrophic extinction event at the boundary of the Cretaceous and Paleogene periods around 66 million years ago. These creatures possessed several key adaptations that allowed them to endure changes in ecosystems. Firstly, their small size gave them an advantage in finding shelter and resources. Small mammals could hide in burrows and crevices, avoiding predators and climatic changes, which helped them survive in conditions where large species, such as dinosaurs, had gone extinct. Additionally, they were omnivorous, allowing them to utilize diverse food sources, including seeds, fruits, insects, and small vertebrates. Studies show that this diet facilitated their rapid reproduction and adaptation to new conditions. Birds also became an important part of the ecosystem, surviving due to their ability to fly, which allowed them to avoid terrestrial predators and find food over large areas. Birds, descended from small dinosaurs, developed feathers for thermoregulation and improved flight, which contributed to their radiation and colonization of various ecological niches. For instance, by the beginning of the Eocene, just a few million years after the extinction event, various bird species adapted to life in forests and open spaces had already appeared in North America. Crocodiles and turtles also survived this extinction, thanks to their ability to withstand long periods of fasting and slow metabolism. These reptiles could remain underwater for extended periods, allowing them to avoid drying up of water bodies and find food in altered conditions. For example, crocodiles could submerge themselves in water for several hours, enabling them to survive in drying ecosystems. Turtles, in turn, developed a hard shell that protected them from predators, allowing them to survive even in areas where resources were limited. As a result, by the beginning of the Eocene, all these groups began to actively spread and fill the vacant ecological niches, leading to significant changes in ecosystems. An example of this is the rapid increase in the diversity of mammals, as evidenced by fossil records showing that the number of species increased geometrically. At this time in North America, the first primitive forms of horses and elephants appeared, beginning to occupy new ecological niches previously unavailable to mammals. Supervolcanoes are colossal geological structures capable of eruptions that can expel hundreds and even thousands of cubic kilometers of magma and other materials. Unlike ordinary volcanoes, which typically eject small volumes of lava, supervolcanoes form as a result of significant accumulations of magma beneath the Earth's crust. When the pressure in the magma chamber reaches a critical point, catastrophic explosions occur, capable of altering the landscape over many kilometers. These eruptions are usually accompanied by the formation of calderas, immense depressions that arise when a portion of the Earth's surface collapses due to the emptying of the magma chamber. Supervolcanoes can have diameters of up to 100 kilometers, making them unique among volcanoes. The eruptions of supervolcanoes can cause significant changes in global climate by releasing enormous volumes of ash and gases, such as sulfur dioxide, into the atmosphere. This leads to the formation of aerosols that can reflect sunlight, causing temporary cooling on the planet. For example, such phenomena can result in a sharp drop in temperature by several degrees, which in turn can affect agriculture and ecosystems worldwide. Supervolcanoes can alter climatic conditions for decades and sometimes even centuries. Research indicates that the eruptions of supervolcanoes can be powerful enough to cause mass extinctions, as evidenced by geological records of previous catastrophes. These events often coincide with so-called global cold snaps, during which significant temperature drops are observed on Earth. An important aspect of supervolcanoes is their ability to trigger tsunamis if an eruption occurs underwater. Data on supervolcanoes are collected using geophysical methods such as seismic sounding and gravimetric surveys, which help scientists understand the structure of magma chambers and predict possible eruptions. In some areas where supervolcanoes are located, hot springs and geysers are observed, which are indicators of the presence of magma beneath the surface. These geothermal manifestations indicate high temperatures and activity, making such regions unique for study. It is important to note that supervolcanoes do not erupt with the regularity of ordinary volcanoes. Their eruptions can occur with intervals of tens of thousands of years, making them unpredictable and potentially dangerous to humanity. Scientists continue to study supervolcanoes to better understand their mechanisms and the consequences of possible eruptions, which is particularly relevant in light of climate change and its impact on our planet. Supervolcanoes can release up to 1 million tons of ash per day, posing serious risks to human health and ecosystems. Yellowstone caldera is one of the largest supervolcanoes on the planet, with a diameter of approximately 75 kilometers. The formation of the caldera occurred after a catastrophic eruption around 600,000 years ago, when the magma chamber beneath the Earth's surface collapsed, leaving a vast crater. This powerful structure hides an enormous reservoir of molten rock capable of ejecting colossal volumes of ash and gas into the atmosphere if a new eruption occurs. Volcanic activity here is not uncommon. Since the formation of the caldera, more than 300 eruptions have been recorded, although most were minor. On the surface of the caldera, numerous hot springs and geysers can be observed, such as the famous Old Faithful geyser, which shoots water up to 30 meters high every 80 minutes. This spectacle attracts millions of tourists, but beneath this picturesque surface lies the power capable of altering the climate of entire continents. Scientists like Dr. Michael Pollan of the US, Geological Survey continue to monitor the caldera's activity using seismic and geodetic methods. Over the past decades, observations have shown that the caldera periodically rises and falls by several centimeters, indicating the movement of magma beneath the surface. The Yellowstone volcanic system contains approximately 90% of all geysers in the world and is home to a unique ecosystem that thrives on geothermal energy. Notably, over the past 3 years, the temperature in several hot springs has significantly increased, which may indicate an increase in volcanic activity. The power hidden beneath the caldera is astonishing. Molten magma can rise to the surface with temperatures exceeding 1,000 degrees Celsius, posing potential threats to the entire region. Nature here is unpredictable, and scientists are constantly researching how climate change may affect volcanic activity. Ultimately, the potential for a new eruption remains a real threat, not only to nearby populated areas, but to the entire North American territory, as in the event of a catastrophic event, the ash could obscure the sun for months. Yellowstone caldera remains one of the most studied volcanoes in the world, and its grandeur underscores the beauty of the surrounding landscape, where nature and the power of the earth intertwine in a unique dance, inspiring awe and fear simultaneously. The last major eruption of the Yellowstone volcano occurred approximately 600,000 years ago and is considered one of the most powerful volcanic events in Earth's history. According to geological data, it resulted in the formation of a caldera with a diameter of about 30 kilometers. The eruption released an enormous amount of volcanic ash, with a total mass estimated at several hundred cubic kilometers. The ash spread over thousands of kilometers, reaching distant areas such as the central part of the United States, where the soil became unsuitable for agriculture and the air became saturated with toxic particles. Within a radius of 500 kilometers from the volcano, vegetation was destroyed under a layer of volcanic material, leading to significant changes in ecosystems. The impact on the climate was also substantial. Studies show that the temperature in North America decreased by several degrees, causing serious problems for animals and plants. This period is known as the volcanic winter, when sunlight barely pierced the clouds of ash, and the world was plunged into semi-darkness. As a result, many ecosystems ceased to exist as they had before. The drop in temperature also led to the inability of some animal species to survive in the new conditions, causing changes in food chains. The volcano, which had been dormant for thousands of years, suddenly altered the landscape and climate, leaving behind only shadows of its former glory. Experts believe that such eruptions could occur again in the future, which causes concern among scientists and ecologists. In recent decades, changes in the behavior of the volcano, such as an increase in temperature in hot springs and the uplift of the land, may indicate increasing activity. It is important to remember that Yellowstone is not only a natural wonder, but also a potential threat to all of North America, where the consequences of its eruption could affect vast territories and the lives of millions of people. Supervolcano Toba is located on the island of Sumatra in Indonesia and is one of the largest volcanoes on the planet. Its caldera has a diameter of approximately 130 kilometers and a depth of up to 1,300 meters. It is the second largest caldera on Earth, formed as a result of a catastrophic eruption that occurred about 74,000 years ago. At that time, the eruption of Toba was one of the most powerful in Earth's history, ejecting around 1,300 cubic kilometers of volcanic material into the atmosphere and causing global climate changes. Historians and geologists believe that this eruption could have led to a sharp decline in the human population, resulting in what is known as a bottleneck in the evolution of Homo sapiens. Within the caldera, a picturesque lake named Lake Toba was formed, with an area of approximately 1,600 square kilometers, making it the largest volcanic lake in the world. The depth of the lake reaches up to 500 meters, and its waters have a characteristic blue color surrounded by green hills and mountains. This creates a striking contrast between the serene landscape and the hidden destructive power that could one day awaken again. Scientists note that Toba continues to be an active volcano, albeit in a state of dormancy, and its potential threat should not be underestimated. In recent decades, research has shown that beneath Lake Toba lie extensive magma sources, indicating the possibility of future volcanic activity. Tourists from around the world come to see this natural beauty, but they are always aware that beneath the calm surface of the water lies power capable of altering the planet's appearance. Local residents living on the shores of the lake also understand the gravity of the situation. They engage in their livelihoods and develop tourism, but always keep in mind that nature can manifest its power at any moment. Around the lake are many villages, and on its shores, one can find ancient temples and monuments that testify to the rich culture of the local population that has inhabited these lands for millennia. Lake Toba is not only a beautiful place, but also an important object for studying volcanic activity, and its history serves as a reminder that even the most tranquil landscapes can hide dangers. In the 18th century, one of the first English colonies was established here, and today this place continues to attract the attention of scientists, adventurers, and nature lovers. The eruption of the Toba volcano, which occurred around 74,000 years ago, was the most powerful known volcanic event in human history. At that time, the volcano ejected more than 1,000 cubic kilometers of ash and gases into the atmosphere, leading to a global catastrophe. Ash enveloped the Earth, blocked sunlight, and caused a sharp cooling. The planet's temperature dropped by several degrees, resulting in what is known as the volcanic winter. This phenomenon lasted for years, possibly even decades. As a result of these climate changes, ecosystems began to shift. Agriculture was threatened, and animals and plants were unable to adapt to the new conditions. According to scientists, the population of early humans at that time was reduced to a few thousand individuals. This demographic catastrophe likely led to a genetic bottleneck that affected all subsequent generations. Studies based on the analysis of the DNA of modern people show that we are all descendants of a limited number of ancestors who survived this terrible event. Archaeological findings indicate that the inhabitants of Southeast Asia who survived this eruption faced severe difficulties in finding food and resources. The impact of Toba was felt far beyond the region. Climate changes affected even remote places like Africa and Europe. Scientists assert that this eruption could have played a significant role in human migration and their adaptation to new conditions. The volcanic activity of Toba served as a catalyst for changes in human evolution, forcing them to seek new ways to survive and expand their habitat. It is not surprising that this catastrophic moment in Earth's history has attracted the attention of not only researchers, but also enthusiasts of antiquity, who are trying to understand how one eruption could have influenced the fate of humanity. The ash ejected by Toba settled over an area that encompasses modern-day Indonesia, Malaysia, and even parts of India, indicating the scale of the catastrophe. The volcanic activity of Toba continued for several thousand years, and by this time, the volcano's formation had changed, resulting in one of the largest lakes in the world, which we see today. The study of Toba shows that nature is capable of such destruction that it can completely change the course of history. Volcanic activity is directly linked to climate changes, creating complex systems of interconnections between Earth's internal processes and its atmosphere. During eruptions, volcanoes release significant amounts of gases into the atmosphere, such as sulfur dioxide, carbon dioxide, and water vapor. Sulfur dioxide, upon entering the atmosphere, forms aerosols that can reflect sunlight back into space. This phenomenon reduces the amount of solar radiation reaching Earth's surface, leading to a decrease in temperature. Studies show that even small changes in the concentration of volcanic gases can cause significant temperature fluctuations on the planet. For example, Aerosols resulting from volcanic activity can remain in the atmosphere for several months to several years, creating a volcanic winter effect, where a decrease in temperature is observed on Earth. At the same time, carbon dioxide emitted by volcanoes plays a contradictory role, contributing to the greenhouse effect. It traps heat in the atmosphere, which can lead to an increase in temperature, especially in the long term. This creates a balance between cooling and heating effects, which depends on the intensity and duration of volcanic eruptions. Climate change models show that during periods of intense volcanic activity, changes in average climate can persist for decades. The Earth's climate system is very sensitive to such changes, and even a slight increase in volcanic activity can affect global climate models. Volcanic aerosols also contribute to cloud formation, which alters the properties of atmospheric radiation. White clouds reflect sunlight, reducing surface heating, while dark clouds absorb heat, which can lead to local climate changes. No less important is the fact that volcanic activity can alter rainfall and wind patterns. Changes in temperature and pressure in the atmosphere due to volcanic gas emissions can cause changes in weather patterns, including an increase in the frequency of extreme weather events. Research shows that in regions directly affected by volcanic activity, both droughts and floods can occur, worsening living conditions for the local population. The Earth's climate system operates on the principle of a closed cycle, where each eruption, gas emission, or temperature change can affect the entire ecosystem. These interconnections become particularly evident in the context of global climate change, where volcanic activity is one of the factors contributing to changes in temperature regimes and atmospheric pressure. For example, in the context of global warming, even short-term volcanic gas emissions can have long-term consequences for the climate. Volcanic activity is not just a local phenomenon, but a powerful factor that can influence climate conditions on a planetary scale. Research shows that during periods of strong eruptions, significant changes not only in temperature, but also in the composition of the atmosphere occur, which in turn affects life on Earth. Volcanic gases and aerosols, by changing the transparency of the atmosphere, directly influence how solar radiation interacts with the Earth's surface. The nature of volcanic activity and its consequences for the climate demonstrate how complex and intricate the system in which we exist is. Studying these processes helps understand how the internal structure of our planet can influence climate changes, which is crucial for predicting the future. Volcanic eruptions have the ability not only to shape landscapes, but also to significantly alter global climate conditions. The year 1816 became known as the Year Without a Summer, and this name is not without reason. Following the catastrophic eruption of the Tambora volcano on the Indonesian island of Sumbawa in April of 1816, the Earth's atmosphere was filled with immense quantities of ash and sulfur. This eruption, one of the most powerful in human history, led to a significant decrease in global temperature. The summer of 1816 was unusually cold. In some regions of Europe and North America, snow fell when flowers were supposed to be in bloom. In July, the temperature in New England dropped to -2 degrees Celsius, which was completely atypical for that time of year. Farmers, expecting a bountiful harvest, faced crop failures. Cold nights and unending rains destroyed the crops. For example, in Germany and Switzerland, potatoes and grains were completely destroyed, leading to food shortages. This resulted in a famine in Europe that affected millions of people. While in some regions there were mass protests due to food shortages, in other places people gathered in groups to share their remaining supplies. Local authorities, not understanding the cause of this strange summer, tried to calm the population, but without success. In the United States, a similar phenomenon was observed. In July, snow fell on the eastern coast, causing confusion and panic. In letters of the time, people discussed how this summer seemed cursed, and they lost hope for a normal life. The famous poet Lord Byron, who was living in Switzerland at the time, even described the gray sky and unending rains in his works, reflecting the mood of the era. People could not understand why nature had gone awry, and many linked the cold to a gloomy omen. In some regions, such as Vermont, the crop yield was reduced by 80% compared to normal years. This led to a large number of deaths from hunger, especially among the poor who could not afford the remaining products. Across Europe and North America, there was a deep crisis, and people sought scapegoats, sometimes even in religious causes. Farmers began to resort to magical rituals, hoping to return to normal weather conditions, while scientists tried to explain the phenomenon from a scientific perspective. Nevertheless, despite all efforts, nature remained merciless, and the year 1816 became a symbol of how fragile our ecosystem is and how difficult it is to predict its reactions to catastrophic events. People from different parts of the world, observing how nature played with them, continued to seek explanations for the strange and unpredictable phenomena that had befallen them without warning. By the end of the year, as the atmosphere began to clear of ash, farmers were still in disarray, and hungry families searched for ways to survive in conditions that seemed completely unbearable. The 18th year of the 19th century was the time when the world confronted the aftermath of a natural catastrophe known as the Year Without a Summer. This event did not merely disrupt the usual course of life, but also had a profound impact on culture and art. During this period, when Europe was shrouded in gray clouds and temperatures dropped to record lows, people felt a sense of despair and anxiety. Mary Shelley, inspired by the atmosphere of gloomy landscapes and apocalyptic moods, wrote her famous novel Frankenstein in 1818. In this work, published in 1818, she explores themes of creation, destruction, and human responsibility, reflecting society's fears about scientific discoveries and their consequences. The novel became a symbol not only of fear of the unknown, but also a warning about how the desire for control over nature can lead to catastrophic results. At the same time, artists of the period, such as John Constable and Caspar David Friedrich, created works filled with dark and dramatic landscapes that reflected the oppressive atmosphere of the time. In Friedrich's paintings, for example, dark forests and gloomy mountains evoke a sense of loneliness and despair, which was characteristic of the moods of people at that time. His work, The Wanderer Above the Sea of Fog, created in 1818, illustrates not only natural disasters, but also the inner turmoil of a person facing the unknown and inexplicable. Literature of the time was also permeated with the theme of apocalypse. Poems by Lord Byron and Percy Bysshe Shelley reflected the fears and hopes born out of the conditions of global climate change. In his poem The Course of the Storm, Byron describes the destructive power of nature on human lives, emphasizing the helplessness of people in the face of nature. Examples of this dark art, created as a result of the catastrophe, became classics, inspiring future generations. The 18th year left its mark on history as a year of climatic anomalies, but it also became a significant milestone in the cultural development of Europe, when creators, artists, and writers used their works to express the fears and hopes of their time. Works created during this period continue to inspire today, demonstrating how nature and human creativity can intertwine in challenging circumstances. The 18th year was a turning point when art reflected not only reality, but also the inner feelings of people, making them think about their place in the world. Glacial periods represent significant stages in the geological history of Earth, when large masses of ice covered substantial parts of continents, altering the climate and landscape. These cycles of glacial advance and retreat have occurred over millions of years, resulting in characteristic landforms. Glaciers, moving slowly but inexorably, carved valleys, shaped mountain ranges, and created lakes. In some places, the width of glaciers reached hundreds of kilometers, and their thickness often exceeded 3 kilometers. Each glacial period was accompanied by changes in the river system. Rivers crossing glacial areas altered their courses under the influence of the ice mass, forming new deltas and lakes. Ice sheets, such as those that covered North America and Eurasia, acted as powerful bulldozers, leveling the Earth's surface and moving vast volumes of sediment. It is known that such changes occur in accordance with the Milankovitch cycle, which includes variations in Earth's orbit and the tilt of its axis, affecting the distribution of solar radiation and climatic conditions. Important factors determining the cycles of glacial periods are changes in atmospheric temperature, which are linked to the levels of carbon dioxide and other greenhouse gases. For example, during the maximum glaciation, temperatures could drop by 10 degrees Celsius compared to current values. Approximately every 100,000 years, significant climatic fluctuations occurred, causing glaciers to advance and retreat, and forests and steppes to alternate. When a glacier reached its maximum extent, it would halt, and for thousands of years, it would retreat slowly. This created new ecosystems that adapted to the changing conditions. For example, after the retreat of glaciers in areas now part of Canada and the United States, forests began to develop, and rivers, previously blocked by ice, started to flow again, forming new ecosystems. Remnants of the glacial period can still be observed today. For instance, in the form of moraines, which are hills formed from rocks and sand left behind by glaciers. These geological formations testify to how glaciers moved and processed materials, altering the landscape of Earth. In places like Scandinavia and Canada, one can find traces of ancient glacial tongues stretching for tens of kilometers, a reminder of the grandeur and power of ice. It is important to note that glacial periods not only changed the physical surface of Earth, but also influenced the development of humanity. Conditions created after the last glacial periods facilitated human and animal migration, ultimately leading to the formation of various cultures and civilizations. For example, archaeological findings show that people began to settle areas freed from ice only a few thousand years ago, when the climate became more favorable for life. Glacial periods continue to be a subject of study for scientists who investigate their impact on global climate and ecosystems. Scientists like Dr. Lee Greenwald from the University of California are studying ice samples from Greenland to understand how past climate changes can help predict the future. Research shows that current climate changes may be linked to the same processes that led to glacial periods. As we observe changes in global temperature today, it is worth remembering that glacial periods have left an indelible mark on Earth, and their study is important for understanding how humanity can adapt to future climatic changes. It is important to remember that glacial periods not only shaped nature, but also people and their interaction with the surrounding world. Data on paleoclimate show that the level of carbon dioxide in the atmosphere was 2 to 3 times lower than it is now, which also affects climatic dynamics. About 20,000 years ago, during the last glacial maximum, Earth was covered by vast ice sheets that stretched thousands of kilometers from the poles to the equator. In northern North America, the ice shield reached heights of up to 3 kilometers, covering territories of present-day Canada and the northern parts of the United States. In Europe, the ice sheet known as the Scandinavian ice sheet covered a large part of Scandinavia, with its front reaching northern Germany and even Britain, creating powerful ice streams. To the south, while ice sheets occupied vast territories, the global sea level was significantly lower, approximately 120 meters below its current level, opening up new lands and allowing humans and animals to migrate through now submerged areas. During this time, Earth's climate zones underwent significant changes. Tundras and steppes replaced tropical forests, and the fauna of the glacial period included giants such as the mammoth, the woolly rhinoceros, and the saber-toothed tiger, which adapted to the harsh living conditions. Mammoths, reaching heights of up to 4 meters and weighing up to 6 tons, inhabited open plains where they could find food in the form of grasses and shrubs. The woolly rhinoceros, with its massive body and thick fur, also thrived in these conditions, while saber-toothed tigers hunted large herbivores using their strength and speed. These animals were not the only inhabitants of the glacial world. Freshwater and lake ecosystems supported life forms such as giant beavers and water buffaloes. The glacial climate fostered the formation of specific ecosystems where diverse plant and animal species adapted to low temperatures and short summer seasons. As a result of powerful glacial erosion, magnificent glacial valleys and fjords were formed, which later became distinctive features of the landscape. However, the climate change that occurred after the retreat of the glaciers was catastrophic for many species that could not adapt to the new conditions. Ultimately, the emergence of modern climate zones and ecosystems was made possible by this global glaciation, which transformed the face of Earth and its inhabitants. Around 12,000 years ago, as the glaciers began to retreat, humanity gained the opportunity to settle new lands and resources, which ultimately led to the development of civilizations. The megafauna of the last ice age, which existed on Earth approximately 30 to 10,000 years ago, represents a captivating example of adaptation to harsh conditions. Mammoths, possibly the most famous of these giants, reached heights of up to 4 meters and weighed up to 600 kilograms. These herbivores were covered in thick fur that protected them from the cold climate. They also had enormous curved tusks, reaching lengths of up to 4 meters, which they used for foraging under the snow and in combat with rivals. Woolly rhinos, another large mammal of this period, could reach weights of up to 2 tons and had fur similar to that of mammoths, making them ideal for life in cold northern latitudes. These rhinos also had massive horns, which they used for defense and foraging. Cave bears, which could reach weights of up to 500 kilograms, were among the largest terrestrial predators of their time. They inhabited caves, where they found shelter from harsh winters, and were adapted to life in tundra conditions. Their diet consisted not only of meat, but also of plant material, allowing them to survive in challenging conditions. Saber-toothed cats, such as Smilodon, were true predators, with their canines reaching up to 25 centimeters. These cats hunted large herbivores like mammoths and rhinos, using their strength and speed. Their strong muscles and adaptation to open landscapes allowed them to successfully hunt fast-moving prey. These giant herbivores supported complex ecosystems, creating spaces for the growth of other plant and animal species. Their movements across landscapes facilitated the spread of seeds and the formation of unique ecosystems that could not exist without their presence. For example, mammoths used their tusks to dig for food, which helped clear the ground of snow and allowed other animals to find food. As a result of their activities, rich meadows with diverse flora developed, providing habitats for many other species. Saber-toothed cats, in turn, played a crucial role in maintaining the balance of the ecosystem by controlling the population of herbivorous animals and preventing their overpopulation. This prevented the depletion of vegetation and contributed to the preservation of biodiversity. The megafauna, therefore, was not just a collection of individual species, but a complex network of interactions where each element had a unique role. The disappearance of these animals due to climate change and human activity led to the destabilization of ecosystems, resulting in significant changes in the biota that existed at the time. The need for adaptation to new conditions led to the extinction of many species, serving as one of the most vivid illustrations of the interaction between humans and nature in history. The megafauna of the last ice age continues to attract the interest of scientists and researchers who strive to understand how these giants could exist and how they influenced their surroundings. Studies of fossil remains found in places like Siberia and North America help reconstruct the picture of their lives and interactions with other species. For example, finds on the territory of modern Yukon show that mammoths coexisted with other megafauna, creating unique ecosystems that no longer exist. All this underscores the importance of megafauna in the ecosystems of that time and their influence on the formation of the landscape we know today. The remains of mammoths and other megafauna are not only scientific finds, but also real windows into the past, allowing us to better understand how life on Earth changed and evolved over millennia. Such finds as frozen mammoth remains allow researchers to study their genetic material, opening new horizons in the study of ancient species and their adaptations. The melting of glaciers at the end of the Pleistocene, which occurred around 11,000 years ago, opened up vast territories previously covered by thick layers of ice. As a result of this process, new landscapes emerged, including large lakes and river systems. For example, the formation of Lake Agassiz in North America was due to the melting of the Laurentide ice sheet, which left behind not only the lake, but also rich soil. The global sea level began to rise gradually, which is linked to the fact that the ice sheets covering Greenland and Antarctica began to actively lose mass. Scientists have calculated that over the period from the end of the last ice age to the present, the sea level has risen by approximately 120 meters. This change also led to significant transformations in ecosystems. With the retreat of ice in the north, forests began to develop actively, gradually replacing tundra and taiga. Research by biologists shows that by the beginning of the Holocene, forests in the territories of modern Canada and Alaska had moved north by up to 300 kilometers compared to previous millennia. At this time, coniferous forests, mainly consisting of spruce and pine, began to occupy areas previously covered by mosses and lichens. This change in flora contributed to the emergence of new ecosystems, where various animal species began to inhabit. For example, squirrels and deer began to actively populate new forest areas, altering food chains and interactions between species. At the same time, the protective ecosystem functions of forests became crucial in holding soil and preventing erosion, which was critically important in the changing climate. Research by paleoclimatologists shows that for several thousand years after the end of the Ice Age, the temperature on Earth continued to rise, contributing to the further expansion of forests. Meanwhile, in some regions, such as Scandinavia, forests reached their maximum extent, while in other areas, such as northeastern Asia, mixed forests formed, combining both coniferous and deciduous trees. These forests became important ecosystems, providing biodiversity and resilience to climate change. Scientific research shows that by the end of the Holocene, which began around 10,000 years ago, forest ecosystems covered more than half of the territory of Europe and North America. Thus, the melting of glaciers not only changed the landscape of the Earth, but also led to colossal changes in ecosystems that shape the face of our planet today. During the melting of glaciers, catastrophic floods occurred, leaving behind devastating consequences. One of the most well-known examples is the breach of the glacial lake of Missouri in North America, which happened around 14,000 years ago. When the glacier began to melt, a massive lake formed, filling valleys that are now known as glacial kettles. When the water pressure reached a critical point, the ice dam could no longer hold, and water burst out with immense force. This sudden release of water caused powerful megafloods that altered the landscape in just a few days. Water, moving at speeds up to 100 kilometers per hour, eroded rocks, creating new canyons and valleys that can be seen in those areas today. One such formation is the Scabland, a specific landscape feature formed by the action of powerful currents. In these places, you can observe extensive terraces and cracks, which are evidence of the immense force of water eroding rocks and soil. An example is the breach of a glacial lake in Greenland in the year 2017, when rapid melting of glaciers led to massive floods that inundated coastal areas and changed the courses of rivers. Water washed away vast tracts of land, and today these changes continue to influence the ecosystems of the region. Scientific research shows that such floods can occur with a periodicity of several hundred years, and their effects remain visible for thousands of years. For instance, the breach of a glacial lake in Scandinavia resulted in the formation of a vast landscape, including deep canyons and eroded rocks, which serve as clear evidence of the power of the water. These events not only shaped the landscape, but also had a profound impact on flora and fauna, altering familiar ecosystems and creating new biotopes. Glacial floods, as a rule, occur suddenly and can last only a few days, but their impact on the landscape can persist for thousands of years. For example, in the region of the Colorado River, where similar events resulted in the formation of canyons up to 1,000 meters deep. These natural disasters continue to be a topic of study in relation to climate changes and their impact on Earth. It is important to note that such breaches not only destroyed existing ecosystems, but also created new ones, which is particularly significant in the context of climate change. At the end of the Pleistocene epoch, around 11,000 years ago, significant changes occurred on Earth that led to the mass extinction of megafauna. Mammoths, mastodons, giant sloths, and numerous other large mammals that once inhabited the vast expanses of the planet disappeared, leaving behind only fossils and mysteries. The main factors contributing to this extinction were climatic changes, triggered by the end of the last ice age, and human pressure, as humans began to settle new territories. As temperatures rose, glaciers retreated, altering ecosystems. Forests grew where open steppes had been, forcing megafauna, adapted to cold and open conditions, to lose their habitats. Mammoths, which could reach heights of over 4 meters and weigh up to 6 tons, depended on grassy steppes and Arctic tundras, which gradually disappeared. Mastodons, their close relatives, preferred more forested areas and also struggled to adapt to the changing conditions. Around 15,000 years ago, humans began to actively hunt megafauna. Archaeological findings show that ancient people used stone tools and prepared meat and hides from these large animals. For example, in the United States, in places like Clovis, tools associated with mammoth hunting have been found. These facts confirm that human impact on ecosystems, along with natural climatic changes, created ideal conditions for the extinction of an entire complex of species. Research indicates that in North America, megafauna went extinct around 3,000 years before the present, while in other regions, such as Siberia, mammoths survived until around 2,000 years before the present. Additionally, giant sloths, which reached the size of modern bears, could not survive the climate changes and human hunting, leading to their final disappearance. This process of megafauna extinction not only altered the ecosystems of the time, but also influenced the further development of human civilization, paving the way for the transition to agriculture and livestock farming. Gradually, ecosystems adapted to the new conditions, but the traces of megafauna remained in the myths and legends of the peoples living in those regions. For example, in northern Europe, stories of large animals that once roamed the lands now covered by forests and fields have been preserved. It is also believed that climatic changes, along with human activity, created conditions for competition between species, further complicating the survival of large mammals. Considering all these factors, it can be asserted that the disappearance of megafauna at the end of the Pleistocene was the result of a complex interaction between climatic changes and human activity. Mammoths and mastodons, which once dominated their ecosystems, became part of history studied by modern scientists. Their extinction was one of the significant events that shaped the face of Earth in the subsequent millennia. Meteorite craters are vivid evidence of the constant interaction between Earth and the cosmic space, and their study reveals numerous mysteries related to the history of our planet. Each crater is a record of an impact that occurred at a specific moment in time, leaving an indelible mark in the geological record. Since the formation of Earth, approximately 4.5 billion years ago, it has been subjected to numerous cosmic impacts. Scientific research shows that on average, about 100,000 tons of meteoritic material enter Earth's atmosphere each year. Only a small fraction of this material reaches the surface as meteorites, while the majority burns up in the atmosphere, leaving behind only light trails. Crater formation occurs when a large meteorite, with significant mass and speed, collides with Earth, releasing enormous energy equivalent to a nuclear explosion. For example, the impact that created the Chicxulub crater in Mexico occurred around 65 million years ago and was one of the causes of the mass extinction of dinosaurs. Research shows that the diameter of this crater is approximately 120 kilometers, and the energy of the impact was several million times greater than the bomb dropped on Hiroshima. These events not only shaped the physical landscape, but also significantly influenced the climate and ecosystems. Craters become temporary windows into the geological history, allowing scientists to study layers of sedimentary rocks that preserve information about events preceding the impact. For instance, research has shown that in the areas of craters, one can find microscopic remnants of life that help understand how surviving organisms adapted to new conditions. Since Earth continues to collide with cosmic objects, the likelihood of such catastrophic events remains relevant. Scientists are actively researching the possibility of predicting such impacts by analyzing the orbits of potentially dangerous asteroids. NASA's database, which tracks objects approaching Earth, currently lists over 7,000 such objects, and this number is constantly growing. In addition, craters can serve as indicators of changes in the geological activity of the planet and help in the study of processes such as plate tectonics. For example, craters formed as a result of ancient collisions can be found in places where tectonic plates move, creating conditions for further research. Each crater is also a call to awareness of Earth's vulnerability to cosmic forces. The energy released during collisions can destroy entire ecosystems and change the climate on the planet, making the study of such phenomena vital for the future of humanity. Scientific research on meteorite craters helps not only to understand the past of our planet, but also to prepare for possible threats in the future. Researchers continue to develop new technologies for the detection and tracking of potentially dangerous objects, which allows for the improvement of the warning system and the minimization of the consequences of possible collisions. In recent years, numerous studies have been conducted, such as the AIDA project, which is aimed at testing the capabilities of deflecting asteroids from their trajectory. These measures underscore the need for active monitoring of the cosmic space, since Earth remains under the constant influence of cosmic forces that can change its appearance at any moment. The study of meteorite craters is not only a scientific interest, but also a matter of survival for future generations. Data on craters can also be used to understand the conditions necessary for the emergence of life on other planets, opening new horizons in the search for extraterrestrial life. The meteor crater, also known as the Arizona crater, is one of the most impressive geological structures on Earth, formed around 50,000 years ago as a result of the impact of a meteorite with a diameter of approximately 25 meters. Located about 130 kilometers northeast of Flagstaff, this crater has a diameter of about 1 kilometer and a depth of around 200 meters, making it the largest meteorite crater in North America. Visually, it resembles a giant wound on the Earth's surface, surrounded by steep walls that expose layers of rock formed over millions of years. Standing at the edge of the crater, one feels the grandeur of the event that created this structure and realizes that it happened relatively recently in geological terms. The landscape around the crater is striking, with its harsh, almost Martian appearance. Rocks and stones covered in red and brown sand, as if they have not changed since the meteorite impact. Around the crater, one can see a profusion of cacti and rare plants, giving the place a unique atmosphere. The scale of the crater is difficult to describe in words. Standing at the edge and looking down, one feels like an ant at the edge of a giant pot created by cosmic forces. Unique geological processes that led to the formation of the crater continue to attract scientists from around the world, who study its structure to understand how similar events occurred on other planets. For example, ancient volcanic processes and fossils have been found in the crater, providing insight into what this area looked like before the meteorite impact. The meteor crater has also become a popular tourist attraction, drawing up to 200,000 visitors each year, many of whom come to see this natural wonder and experience the atmosphere of an ancient cataclysm. There is even a museum dedicated to the crater, where one can learn about its history, as well as about meteorites and their impact on Earth. Research shows that such craters could have formed not only on Earth, but also on the Moon, Mars, and other planets, making the study of the meteor crater important for understanding our solar system. The crater serves not only as a subject of scientific study, but also as a reminder of how fragile our planet is in the face of cosmic threats. The Popigai crater is located in a remote and inaccessible region of Siberia, at an altitude of approximately 1,000 meters above sea level, and is one of the largest impact craters on Earth, formed about 46 million years ago as a result of a collision with a meteorite about 4 kilometers in diameter. This crater has a diameter of more than 130 kilometers and a depth of about 1 kilometer, making it a remarkable object for studying processes related to cosmic impacts. The uniqueness of the Popigai crater lies not only in its size, but also in the rare impact diamonds that formed as a result of the catastrophic impact. These diamonds, known as impact diamonds, are formed under extreme pressure and temperature conditions that arise during the collision and can contain interesting inclusions, such as minerals that are not typically found in the Earth's crust. Research conducted in the early 2000s by a group of geologists led by Professor Anatoly Podobedov showed that the crater contains significant reserves of these diamonds, which could be of interest not only to scientists, but also to the jewelry industry. The composition of impact diamonds is unique. They differ from ordinary natural diamonds in having a lower crystallographic structure and differing in color, which is related to the conditions of their formation. In addition, the crater is a valuable source of information about the geological history of the Earth. as it has preserved layers of sedimentary rocks that provide insight into the climatic conditions and ecosystems that existed at that time. Research shows that in the vicinity of the crater, traces of ancient ecosystems can be found, including the remains of plants and animals that lived there before the impact. The Popigai crater is also surrounded by taiga forests, where rare animal species such as the Amur tiger and the Far Eastern leopard inhabit, making it not only an object of scientific interest, but also an important natural reserve. In the extreme north, where temperatures can drop below -40 degrees Celsius in winter, visiting the crater becomes a real challenge for researchers, and only the most resilient researchers dare to undertake this. The Popigai crater, which has preserved the traces of a cosmic catastrophe, continues to attract the attention of scientists and nature lovers, representing a unique combination of natural beauty and historical significance. The unique impact diamonds found in the crater have high scientific value, as their study helps to understand the processes that occurred in the Earth's interior. The Tunguska event occurred on June 6, 1908, over a remote taiga in Siberia, when a large cosmic body, presumably a meteorite, entered the atmosphere and exploded with colossal force, equivalent to several megatons of TNT. This explosion led to the destruction of more than 2,000 square kilometers of forest, uprooting trees and creating peculiar labyrinths of fallen trunks that can still be observed in this region. The uniqueness of the event lies in the fact that, despite the extent of the destruction, no crater was found that could indicate the impact site. This became one of the greatest scientific paradoxes of the 20th century. Researchers, starting with the first expeditions, faced numerous difficulties, including the remoteness of the area and the harsh climatic conditions of Siberia, which significantly complicated the search for evidence. 80 years later, in 1999, a group of scientists led by Professor Anatoly Grigorievich Vinogradov conducted extensive research on the Tunguska event. But even they were unable to find conclusive evidence about the nature of the explosion. Scientific debates about the origin of this phenomenon continue, and various hypotheses, including the idea of a comet explosion or a nuclear explosion, only fuel the interest in this mysterious event. Scientific expeditions to the taiga find not only traces of the catastrophe, but also mysterious anomalies, such as abnormally high levels of radiation in certain areas, which only add to the theories of conspiracy and scientific disputes. Interest in the Tunguska event does not wane, as it attracts not only scientists, but also adventure seekers, mystery hunters, and nature lovers. It is interesting that in this region, reports of unidentified flying objects continue to be recorded, which further intensifies the interest in studying the Tunguska event and its aftermath. The Siberian taiga remains one of the most inaccessible places on the planet, making each new expedition a challenge for researchers striving to unravel the mysteries hidden beneath its cover. The Tunguska event became a catalyst for the development of new directions in astronomy and geology, as scientists began to more actively study cosmic objects and their influence on Earth. According to scientists, the energy released by the explosion could have destroyed an entire city, which confirms the scale of the tragedy. In recent decades, attention to the Tunguska event has increased due to the development of technologies that allow for more accurate research, including satellite imagery and georadars. All these facts emphasize that the mystery of the Tunguska event remains unsolved and continues to attract the interest of scientists and lovers of mysteries. February 15, 2013, became a historic day for Chelyabinsk when local residents witnessed a bright flash in the sky at around 9 a.m., which quickly turned into a fiery ball that pierced the atmosphere and fell to Earth. This meteorite, weighing approximately 14,000 tons, entered the atmosphere at a speed of around 18 kilometers per second, causing a shockwave that resulted in damage in the city. The shockwave, according to experts, was equivalent to a trotyl explosion of about 400 kilotons, leading to the destruction of more than 7,000 buildings, including schools, hospitals, and residential homes. Windows shattered to a distance of hundreds of meters, and some buildings sustained severe damage, leaving over 1,500 people injured. Local authorities, recognizing the magnitude of the disaster, began emergency measures to locate fragments of the meteorite. Over the course of several days, groups of researchers and volunteers noticed the Chelyabinsk Lake, where they believed large fragments might be found. Soon, a fragment weighing about 1.5 kilograms was discovered at a depth of around 7 meters, confirming the hypothesis that the meteorite had landed there. The uniqueness of this discovery lay in the fact that it was the first time a meteorite that fell on Russian territory was found with such detailed information about its fall. In the following months, researchers from various countries, including scientists from the USA and Europe, gathered in Chelyabinsk to study the meteorite fragments. Analysis revealed that the meteorite belonged to the chondrite class and contained a high concentration of iron and nickel, making it valuable for studying planetary formation. The data recorded about the meteorite's fall became the basis for numerous scientific studies, placing Chelyabinsk at the center of the global scientific community's attention. These events served as a vivid reminder of how cosmic threats can intrude into everyday life. The Chelyabinsk meteorite demonstrated that even in the 21st century, with advanced technologies and scientific discoveries, humanity remains vulnerable to the cosmos. Discussions about the need for monitoring near-Earth objects and developing protection measures against potential threats became more relevant than ever. The total number of fragments found as a result of search operations exceeded 700, further confirming the scale of this cosmic event. Moreover, the meteorite became a symbol of unity for the residents of Chelyabinsk, who, despite the destruction, came together in their efforts to rebuild their city and unravel the mystery that came from the sky. Tsunamis are powerful ocean waves that arise due to underwater earthquakes, landslides, or even impacts from celestial bodies. The mechanism of their formation begins with the movement of tectonic plates, where one plate descends while another rises, causing a sudden displacement of water. This displacement can create a wave that, despite its immense power, may be virtually invisible in the open ocean. Once the wave leaves the deep ocean zone, it can grow to a height of only a few dozen centimeters. However, as it approaches shallow water, the water's agitation increases, compressing and rising, resulting in the wave reaching heights of several dozen meters. For instance, in some cases, tsunami waves can exceed 30 meters when they hit the shore. This happens because, as the wave transitions to shallow water, its speed decreases, but its energy and height accumulate, leading to catastrophic consequences. Moreover, tsunamis can consist of multiple waves, with the first wave not always being the highest. This creates an illusion of safety, as more powerful waves may follow the initial impact. Such waves can destroy buildings, sweep away cars, and cause extensive flooding. Research shows that the speed of tsunamis in the open ocean can reach 100 kilometers per hour. But on shallow water, this speed decreases, yet the destructive force remains. Approximately 80% of tsunamis occur in the Pacific Ocean, where tectonic activity is most intense. This phenomenon poses a significant threat to coastal areas, where the population often fails to recognize the danger posed by this natural catastrophe. Since waves can occur suddenly, tsunami warnings may not reach residents in time, making them particularly vulnerable. To better understand the nature of tsunamis, it is important to note that they can be caused not only by earthquakes, but also by underwater landslides, which typically occur due to disruption of the stability of the seabed. These landslides can cause instantaneous water movements, creating waves that also have the potential for destruction. Unlike ordinary waves that we observe on the surface of the sea, tsunamis carry immense energy capable of destroying entire cities. As a result of this natural phenomenon, history has recorded numerous tragic events where entire communities were swept off the face of the earth. The tsunami in the Indian Ocean in 2004 became one of the most devastating natural disasters in history, claiming the lives of more than 200,000 people. It was caused by a powerful earthquake of magnitude 9 that occurred on December 31st, 30 kilometers off the coast of the Indonesian island of Sumatra. This earthquake was one of the strongest recorded in history and triggered sudden shifts in the ocean floor at a depth of 6 kilometers. As a result, giant waves began their journey across the Indian Ocean at speeds up to 400 kilometers per hour, comparable to the maximum speed of a jet aircraft. At sea, these waves could reach a height of only 1 meter, making them almost imperceptible to ships. However, as the tsunami approached the shore, it encountered changes in the underwater terrain and the shape of the coastline, causing the waves to suddenly increase in height. On many coastlines, such as Sri Lanka and the southern coast of India, the waves reached heights of up to 30 meters, sweeping away buildings, trees, and everything in their path. The most severe damage occurred in the Indonesian province of Aceh, where the waves crashed onto the shore with incredible force, flooding entire villages and leaving only ruins behind. Following the initial wave, several receding and advancing waves made rescue operations more difficult. According to the UN, around 5 million people were left homeless, and numerous international humanitarian organizations launched large-scale efforts to provide assistance. The regions most affected were not only Indonesia, but also countries such as Thailand, the Maldives, India, and even Somalia, located thousands of kilometers from the epicenter. In Thailand, particularly on the tourist islands of Phuket and Krabi, the waves destroyed the tourist infrastructure, causing billions of dollars in damage. In the aftermath of the disaster, a tsunami early warning system was established in the Indian Ocean, now covering more than 30 countries and helping to minimize the impact of future natural disasters. This catastrophe also led to international cooperation in the fields of seismology and oceanography, contributing to the improvement of scientific methods for predicting and responding to such threats. The tsunami of 2004 had a devastating impact on the ecosystems of the coastal regions of Southeast Asia, particularly on mangrove forests and coral reefs, which play a crucial role in maintaining the marine biosphere. As a result of powerful waves reaching heights of up to 25 meters, mangrove forests, which protect coastlines from erosion and serve as habitats for numerous marine species, were destroyed over an area of approximately 500 square kilometers. These forests, located along the coast, were subjected to flooding and destruction, which negatively affected their ability to restore the ecosystem. Coral reefs, which are home to more than 25% of all marine species, were damaged by the mechanical impact of the waves, as well as subsequent changes in water temperature and salinity. Studies show that more than 70% of the reefs in the affected area were damaged, which worsened the condition of the underwater ecosystem and reduced biodiversity. Salt water that seeped into the soil after the tsunami led to the salinization of agricultural lands, which in turn negatively impacted food production in the region, forcing local farmers to seek alternative agricultural methods. In some areas, the soil salinity increased by 30%, making it impossible to grow traditional crops such as rice and mango. The change in the coastal landscape led to the formation of extensive sandbars, which also made life difficult for local communities. The restoration of natural systems after this catastrophe was a long and complex process. For example, in Thailand, where efforts were made to restore mangrove forests, it can take up to 5 years to restore 1 hectare of mangroves. At the same time, scientific research conducted by scientists from the University of Bangkok showed that with proper attention and support from local communities, these ecosystems can recover faster than expected. The restoration of coral reefs occurs through a process of regeneration, which can take from 10 to 30 years, depending on the environmental conditions and the availability of suitable conditions for the growth of new corals. For example, in the area of Phuket Island, efforts were made to restore coral reefs, where local ecologists began planting young corals to accelerate the restoration process. These efforts involve not only biological rehabilitation, but also social rehabilitation, supporting the local population in their efforts to restore lost resources. It is important to note that climate change can affect the restoration of ecosystems, as it is already leading to an increase in ocean temperatures and changes in the oxygen content of water. For example, over the past 30 years, the water temperature in this region has significantly increased, which can slow down the process of coral recovery. Ecosystems that were destroyed as a result of the tsunami are still in the process of restoration, and it is up to human efforts to determine how successfully they will adapt to new conditions. It is important that local communities and governments continue to work on the restoration of ecosystems, taking into account both ecological and social aspects. Restoration will be long, but it is necessary for preserving the natural wealth of the region and ensuring the sustainable development of local communities. Restored mangrove forests can serve as protection against future floods, and healthy coral reefs can serve as the basis for fisheries and tourism. Scientific research shows that a sustainable approach to ecosystem restoration can not only help nature, but also improve the lives of people who depend on these resources. So the work on restoration continues. Palaco tsunamis are ancient tsunamis that have left significant traces in the geological record of our planet. Geologists study these traces by analyzing deposits formed as a result of powerful waves crashing onto coastlines. Specifically, they examine layers of sand and gravel that can indicate ancient tsunamis. These deposits often contain characteristic fossil remains, such as marine mollusks and even organic materials that can be dated using radiocarbon analysis. For example, in 2009, a group of scientists led by Dr. Hiroshi Sasaki from Tokyo University discovered tsunami deposits older than 3,000 years along the Japanese coast. The study of these layers allows scientists to assess the frequency and magnitude of tsunamis in the past. By comparing data on the size of deposits and their distribution in the geological layer, they can determine how often such events occurred and how strong they were. For instance, the thicker and wider the layer of sand, the more powerful the tsunami was likely to have been. These insights are crucial for risk assessment in contemporary conditions. Based on the studied data, models can be created to predict the likelihood of future tsunamis and their potential impact on populated areas. For example, following the devastating earthquake in the Indian Ocean in 2004, scientists began actively applying the results of paleo-tsunami research to improve tsunami warning systems in the region. In Indonesia, where the consequences of tsunamis were catastrophic, paleo-tsunami research helped create more accurate models for risk prediction. These data also enable the construction of safer buildings and infrastructure, which is particularly important for coastal regions. Thus, the study of paleo-tsunamis not only helps understand past events, but also serves as a valuable tool for protecting the population from future threats. As a result, geologists and climatologists continue to actively investigate paleo-tsunamis to gain a more comprehensive understanding of atmospheric and oceanic processes that influence our future. In such research, scientists from different countries participate, and their work becomes increasingly important in light of climate change and the increasing frequency of extreme weather events. For example, in 2020, an international team of researchers discovered paleo-tsunami traces on the coast of Chile, confirming the theory that this region has historically been subject to strong tsunamis and will continue to be in the future. Earthquakes are sudden and powerful phenomena that occur as a result of the rapid displacement of blocks of the Earth's crust along geological faults. These faults, or tectonic plates, are large sections of the lithosphere that move, collide, or diverge from each other. When sufficient stress accumulates between the plates, it can cause their sudden displacement, releasing energy in the form of seismic waves. These waves travel through the Earth's crust at different speeds, creating oscillations that can be felt on the surface. There are several types of seismic waves: primary P waves, secondary S waves, and surface waves. P waves are compression and rarefaction waves that travel through both solid and liquid media, making them the fastest and the first to reach seismographs. S waves, which follow them, travel only through solid materials, causing lateral oscillations that can be particularly destructive. Surface waves, in turn, travel along the Earth's surface and create the strongest and longest-lasting oscillations, often leading to significant damage to buildings and infrastructure. The suddenness of earthquakes makes them particularly dangerous. While predicting their exact time and location remains a complex task, seismologists use various methods, including the analysis of historical data and the monitoring of stresses in the Earth's crust, to assess the risks. However, even the most advanced technologies cannot guarantee the predictability of seismic events, creating a constant threat to life and property. Earthquakes can cause extensive damage over large areas, leading to human casualties and economic losses. For example, an earthquake with a magnitude of 6 on the surface can cause oscillations of up to 1 meter, which can destroy buildings, bridges, and roads. The perception of the strength of oscillations depends on many factors, including geological conditions, types of structures, and the distance to the epicenter. There is also the phenomenon of secondary effects, such as landslides and tsunamis, which can occur after the main shock, exacerbating the scale of the disaster. Scientific research shows that in some regions, such as the Pacific Ring of Fire, earthquakes occur much more frequently than in other places due to active tectonic activity. For example, in Japan, where several plates collide, thousands of small tremors are recorded annually, and government agencies develop special programs to increase public readiness for potential disasters. The study of earthquakes remains a priority for scientists, as understanding the mechanisms of their occurrence and consequences can help minimize damage and save lives. The cost of post-earthquake reconstruction can run into billions of dollars, and the time required for recovery can take years. In some cases, such as the 2010 earthquake in Haiti, which claimed the lives of more than 200,000 people, the effects are felt for decades. The Great Lisbon Earthquake, which occurred on November 1, 1755, was one of the most devastating natural disasters in European history. The earthquake measured 8.0 on the Richter scale, causing massive destruction in Lisbon and its surroundings. Within minutes, more than 30,000 buildings, including churches, palaces, and residential homes, were destroyed, plunging the city into chaos. Modern researchers estimate that the death toll ranged from 30 to 100,000 people, many of whom perished under the rubble or due to panic. Soon after the earthquake, a powerful tsunami struck, with waves reaching heights of 10 meters, flooding coastal areas, and adding thousands more to the death toll. Fires that broke out in the city spread rapidly, consuming the remaining buildings and continuing for several days, further devastating Lisbon. This event not only shook the city's inhabitants, but also resonated throughout European society, sparking philosophical debates about the nature of evil, divine providence, and human destiny. Philosophers like Voltaire began to question why good people suffer from such catastrophes, challenging traditional religious views of the world. As a result, new ideas emerged, suggesting that evil might not be a result of divine punishment, but a part of the natural order. The Lisbon earthquake also served as a catalyst for the development of seismology as a science. Scientists began to pay more attention to studying earthquakes, developing methods for predicting them and investigating their causes. The reconstruction of Lisbon took many years, and by 1756, work began on a new city plan designed by the Marquis de Pombal, which included stricter building codes and regulations aimed at preventing similar catastrophes in the future. Ultimately, this event not only transformed Lisbon's appearance, but also significantly influenced the development of science and philosophy in Europe. In the night from April 28th to April 29th, 1906, San Francisco experienced one of the most devastating earthquakes in the history of the United States. The epicenter of this catastrophic event was located along the San Andreas Fault, which runs through the entire state of California. The magnitude of the underground tremors reached 8 on the Richter scale, causing massive destruction not only in the city itself, but also in its surroundings. Streets shook, buildings collapsed with a roar, and old brick structures, built without consideration for seismic activity, turned to dust instantly. More than 30,000 buildings were destroyed, and estimates suggest that around 200,000 people were left homeless. However, the destruction caused by the seismic activity itself was just the beginning of the calamities. One of the most serious problems arose from the damage to gas pipelines, which led to numerous fires that engulfed the city. The flames spread in a matter of minutes, and in the chaos, fire brigades were unable to control the fire that quickly spread throughout the city. Due to the damage to the water supply systems, firefighting became virtually impossible. As a result, the fire destroyed more than 6,000 buildings, including entire neighborhoods, leading to greater damage than the earthquake itself. People in panic fled their homes, saving only the most essential items, and sought refuge from the raging flames. Hundreds of people were trapped when their homes burned down completely, and rescue efforts were unable to reach them due to collapsed streets and fallen trees. For several days after the disaster, the city turned into a sea of fire, and an atmosphere of chaos reigned everywhere. Local authorities, trying to cope with the situation, organized the evacuation of the remaining residents, creating refugee camps. About half of the city's population was forced to leave and seek shelter in neighboring cities. The earthquake and fires claimed the lives of more than 3,000 people, making it one of the most tragic pages in the city's history. The reconstruction of San Francisco began almost immediately, but the extent of the destruction was so great that the process took many years. As a result of this event, the city not only changed its architectural appearance, but also became an example for many other cities, where the need for strict building codes and regulations became obvious. In response to devastating earthquakes, architects and engineers began actively developing earthquake-resistant construction to protect lives and minimize damage. One of the first significant steps in this direction was the creation of buildings using the principle of damping. In the early 1990s, Japanese engineers developed a damping system that included special dampers capable of absorbing vibrations caused by earthquakes. These devices are typically installed between the foundation and the building to reduce the transfer of energy from seismic waves to the structure. The use of such technologies significantly reduced the risk of building collapse in seismic zones, as demonstrated by the example of Tokyo after the 2011 earthquake. Flexible structures also play a crucial role in earthquake-resistant construction. Engineers are learning to use materials that can deform without breaking. For example, steel and special polymers allow for the creation of buildings that can bend during seismic activity, absorbing part of the energy. In the 2000s, the famous Torre Arc Tower was built in California, which uses a flexible structure to ensure earthquake resistance, making it one of the safest buildings in seismic-prone areas. Modern technologies also allow the use of special materials such as fiber cement and carbon fibers, which significantly increase the strength and stability of buildings. In the Silicon Valley in 2000, a series of office buildings were constructed using carbon fibers as reinforcing elements, which reduced their weight while increasing their resistance to seismic effects. Research shows that buildings constructed using these technologies can withstand loads 3 times greater than the average for seismic regions. Engineers are also implementing smart construction systems that use sensors to monitor the condition of buildings in real time. These systems can predict vibrations and provide signals for evacuation. In the 2000s, a program was implemented in Chile, where such sensors were installed in new residential complexes, significantly reducing the risk of casualties in case of earthquakes. Scientific research shows that proper design and the use of new technologies can reduce the risk of destruction by 80%. For example, in 2006 in Nepal, after a strong earthquake, new building codes were applied, allowing for the reconstruction of housing with seismic resistance. The results showed that only 30% of buildings constructed according to the new standards were damaged, while older structures were often completely destroyed. Gradually, more countries are adopting earthquake-resistant standards and regulations, confirming the need to adapt urban construction to natural disasters. In Italy, after the devastating earthquake in 2009, strict norms were introduced for new buildings, including the use of damping systems and flexible structures. Research shows that such measures have significantly reduced the number of destructions in seismic-prone areas. As a result, the implementation of modern technologies and design methods has become not just a necessity, but an important step towards ensuring the safety of the population. Global practice shows that earthquake-resistant construction is not only a response to the challenges of the time, but also a guarantee of the future in the face of a changing climate and increasing seismic activity. Early warning systems for earthquakes consist of complex networks of seismometers that continuously monitor the activity of the Earth's crust. These devices are located in areas with high seismic activity, such as Japan, where, according to the Japan Meteorological Agency, there are more than 4,000 seismometers. Seismometers record the movements of the Earth and transmit data in real time to information processing centers. For example, the Earthquake Alert System in California uses more than 7,000 seismic sensors that can detect tremors just a few seconds before they occur. Data processing algorithms, such as Shake Alert, can analyze and interpret information from seismometers using machine learning methods. These algorithms can distinguish between primary P waves and secondary S waves, with the latter causing the most damage. If the system detects an impending earthquake, it triggers an alert that can be transmitted within a few seconds. In Japan, for instance, local services use the JMA system, which can warn the population about an impending earthquake 10 to 20 seconds before it starts, potentially saving thousands of lives. Alerts are sent to mobile phones, public alert systems, and even televisions. A crucial aspect is that each alert must be as timely as possible, as every second counts. According to the U.S. National Geological Service, in the case of earthquakes lasting less than 30 seconds, each moment can be crucial for choosing a safe location. Methods of warning the public include not only text messages, but also sound signals that are activated in public places such as schools and stadiums. In some cases, the system can automatically close gas valves and shut off electricity in buildings to prevent potential fires. In Japan, where earthquake preparedness is at an extremely high level, regular drills are conducted to prepare the population for real threats. Millions of people participate in these drills, allowing them to practice safe sheltering in designated shelters, even in conditions of panic. Early warning systems for earthquakes are becoming increasingly important in the context of global warming and increased seismic activity, making them an integral part of strategies to ensure public safety. There are even plans to integrate these systems with other technologies, such as drones, which can quickly assess damage and assist in rescue operations after earthquakes. For example, after a powerful earthquake in Chile in 2015, numerous modern technologies were implemented to improve early warning and emergency response systems. As a result, people have the opportunity to take shelter in safe places in advance and minimize the risk of injuries and losses. It is important to note that each new system requires significant investments and continuous updates to remain effective in the face of modern challenges. The climate of Earth throughout its geological history has undergone numerous changes that can be easily compared to the fluctuations on massive American roller coasters. There have been periods when the planet was in a greenhouse state, characterized by high temperatures, abundant carbon dioxide in the atmosphere, and the absence of glaciers, which in turn facilitated the rapid development of tropical forests and diverse flora and fauna. For example, approximately 100 million years ago, during the Cretaceous period, the temperature on Earth was 10 degrees higher than today, allowing dinosaurs and other reptiles to thrive in the mild climate. These warm periods alternated with cold periods when glaciers covered vast territories, as was the case during the last glacial maximum about 20,000 years ago. During this time, sea level dropped by more than 100 meters below the current level, and extensive areas of North America and Eurasia were covered with thick layers of ice. This contrast in climate conditions demonstrates the dynamism of Earth's climate system. Temperature changes occur due to various factors: tectonic processes, volcanic activity, changes in solar activity, and even fluctuations in Earth's orbit. For instance, according to research by paleoclimatologists such as Dr. Julia Kulik, changes in the tilt of Earth's axis led to significant temperature fluctuations, causing both warming and cooling periods. Over millions of years, Earth transitioned between different climate regimes, and these changes have continually influenced ecosystems and the distribution of species worldwide. It is worth mentioning that during the period between 30 and 16 million years ago, in the Eocene, temperatures were so high that tropical forests extended to the polar regions. However, just a few million years later, in the Miocene, Earth experienced significant cooling, leading to the formation of glaciers in Antarctica. These temperature fluctuations create a constant sense of climate variability, where each new period is a response to previous conditions. Earth, as a living organism, continues to evolve, and its climate system is always in motion, as evidenced by scientific data on multiple cycles of glaciation and warming that have occurred over the past 2 million years. Scientists such as Dr. James Hansen note that these changes occur on timescales that are completely unrelated to human life. These climate fluctuations include not only temperature changes, but also impacts on sea level, humidity, and atmospheric conditions, which in turn significantly affect the biosphere and humanity. It is important to understand that Earth's climate system is not a static state, but a constantly changing phenomenon that requires continuous study and adaptation. For example, the ice caps that currently cover Greenland and Antarctica could disappear, as they have in the past, when temperatures reached critical levels. Approximately 80,000 years ago, during the height of the last ice age, the area covered by ice reached its maximum, and glaciers flooded large land areas. This historical context allows us to understand that climate has always been in a state of change, and therefore, humanity must be prepared for future challenges related to climate fluctuations. In this context, it is important to note that the temperature on Earth can fluctuate by tens of degrees over relatively short periods. Over the past 100 years, the average temperature on the planet has increased by 1 degree, which has serious consequences for ecosystems and the climate as a whole. The Paleocene-Eocene thermal maximum occurred approximately 56 million years ago and was one of the most significant climatic events in Earth's history. This sudden warming led to an increase in ocean surface temperature by 5 to 8 degrees Celsius. As a result, the climate became more tropical, profoundly impacting both marine and terrestrial ecosystems. For instance, the temperatures in the oceans facilitated the expansion of tropical organisms' ranges, such as corals and seaweeds, leading to an increase in marine ecosystem diversity. Coral reef formation reached its peak, as warm waters became ideal for their growth. On land, this warming promoted the spread of broad-leaved forests, which covered significant parts of North America and Europe. Plants like magnolias and palms began to populate areas previously dominated by cold-tolerant species, leading to significant changes in ecosystems and providing new niches for various animal groups. Mammals, such as primitive ancestors of modern predators and herbivores, began to adapt to the changing conditions. Fossil remains indicate that some species, like early forms of mammals, increased in size and diversity, while other groups, such as dinosaurs, had already gone extinct. During this time, there was also active development of marine mammals like whales, which began to transition to a marine lifestyle. The diversity of fish and marine mollusks also increased, as evidenced by fossil findings in various geological layers. There was a significant impact on the carbon cycle. Emissions of carbon dioxide and methane from underwater sources in the oceans accelerated the warming, creating a vicious circle. It is important to note that this event did not pass without consequences. Mass extinctions of species occurred in the context of climate change. Changes in ocean temperature and oxygen levels led to the extinction of certain marine groups, such as specific types of brachiopods and mollusks. Studies suggest that this warming could have lasted for several 100,000 years before the climate began to gradually stabilize. Notably, the Paleocene-Eocene thermal maximum was a crucial milestone in the evolution of life on Earth, as it provided a boost to the development of modern ecosystems. It is important to remember that similar mechanisms leading to rapid temperature changes can be observed today, highlighting the significance of studying this period. The causes of the Paleocene-Eocene thermal maximum are significantly linked to the massive release of methane from methane hydrates on the ocean floor. These methane hydrates, which are crystalline structures formed from water and methane, exist in a stable state at low temperatures and high pressures, characteristic of deep-sea conditions. As ocean temperatures began to rise, this led to the breakdown of methane hydrates, resulting in the release of enormous volumes of methane into the atmosphere. Studies show that the methane levels in the atmosphere increased several-fold, triggering a positive feedback loop. With each methane release, the temperature continued to rise, causing further breakdown of methane hydrates and creating a chain reaction that temporarily destabilized the planet's climate system. Scientists from the University of California, including Dr. John Hopkins, conducted models demonstrating that even a small temperature change could initiate this process. As a result of these changes, the Earth's temperature rose by several degrees, and according to some estimates, during the Paleocene-Eocene maximum, temperatures could reach 30 degrees Celsius in equatorial regions. This led to significant changes in ecosystems, including the extinction of some species and the emergence of new ones. There is also evidence that such methane releases occurred over millions of years, but it was during this period that they reached their peak. This was not just a gas release, but a catastrophic change in climatic conditions that affected the entire planet. It is important to note that methane is a more potent greenhouse gas than carbon dioxide, several dozen times more powerful, which means that its increase in the atmosphere had a significant impact on the greenhouse effect. Therefore, as a result of this process, the climate system was in a state of stress, where each new temperature change became a catalyst for subsequent greenhouse gas releases. Scientific data also indicate that during this period, the level of carbon dioxide in the atmosphere rose to 80 parts per million, which also contributed to global warming. These events provided the basis for understanding how the climate can react to sudden changes in the composition of the atmosphere, which in turn underscores the importance of monitoring current greenhouse gas emissions. Scientific research shows that even contemporary methane releases from agriculture and fossil fuels can lead to similar effects as those observed in the past. Snowball Earth is a hypothetical state of our planet, when glaciers covered almost the entire surface, including equatorial regions. This period, which may have occurred around 82 million years ago at the end of the presumed Cretaceous period, was characterized by extreme climate conditions. Oceans froze almost to the equator, forming ice shields several kilometers thick. Surface temperatures on Earth dropped to minus 40 degrees Celsius, and photosynthesis in most ecosystems virtually ceased. Most plants and animals could not adapt to this harsh climate, and only a few managed to survive. Life persisted in isolated refuges, hot springs, deep-sea hydrothermal vents, and subglacial lakes, where temperatures remained high enough to support life. For example, such conditions could have supported unique ecosystems, as seen today in deep-sea vents where bacteria use sulfur as an energy source. Research indicates that during this time, only the hardiest organisms could survive, such as certain types of archaea and extremophile bacteria. These microorganisms could adapt to conditions that would have destroyed most other forms of life. However, even in these harsh conditions, temperatures were insufficient to sustain traditional ecosystems like forests or grasslands. The freezing of oceans led to a decrease in atmospheric carbon dioxide levels, making it impossible to maintain the heat necessary for life as we know it. The entire biosphere was threatened, and only small niches in the form of hot springs remained places where life could continue. In these hot springs, unique ecosystems could develop based on thermophilic microorganisms that used heat and minerals emerging from the Earth's interior. These conditions resemble modern ones found in places like Yellowstone National Park's geysers, where life thrives in extreme conditions. As the climate changed, eventually leading to the melting of glaciers and the restoration of more familiar ecosystems, the consequences of Snowball Earth were felt for millions of years in the form of changes in the distribution of species and ecosystems. Periodic climate changes like this remind us of how greatly global climate conditions influence life on the planet. Scientific research continues to study these hypothetical periods to understand how they could have influenced the evolution of life on Earth and how similar conditions might arise again in the future. As a result of global climate changes caused by volcanic activity, the process of exiting the Snowball Earth state begins. Volcanic eruptions, such as the eruption of the Toba volcano around 70,000 years ago, release a massive amount of carbon dioxide and sulfur into the atmosphere, leading to a significant increase in the concentration of greenhouse gases. Carbon dioxide, accumulating in the atmosphere, begins to intensify the greenhouse effect, which in turn leads to an increase in global temperature. This is similar to closing the windows of a car on a scorching day. The temperature inside starts to rise rapidly. As the temperature rises, there is a rapid melting of ice that previously covered a large part of the Earth's surface. For example, the ice sheets of Greenland and Antarctica are losing their masses at a rate exceeding several 100 billion tons per year. As a result, even more methane, frozen in the permafrost, is released, further intensifying the climate system. Approximately 80,000 years ago, when the climate system began this dramatic transition, the temperature could have risen by 10 degrees Celsius in just a few thousand years. These are not just small changes. They are catastrophic shifts that affect all ecosystems and species living on the planet. As a result of this process, we see how the world, previously covered in ice and snow, begins to transform into warmer and more humid conditions. An example of such a transformation is the transition from the last ice age to the current interglacial climate, which occurred approximately 3 million years ago when the temperature began to rise and the ice sheets began to retreat. This process was uneven and accompanied by numerous climate fluctuations, but in the end, it led to the formation of modern ecosystems. In particular, this transition led to the formation of tropical forests in some regions that were previously covered in ice. Volcanic activity can also cause temporary climate changes, as it did during the eruption of the Krakatoa volcano in 1883, when the ash and gas released into the atmosphere temporarily lowered the temperature on the planet. This mechanism, where volcanic activity triggers a chain of events that change the climate, demonstrates how fragile our planet is and how quickly it can change. Therefore, exiting the snowball Earth state is not just a slow process, but a rapid and dramatic transition that can change life on Earth in just a few decades. As a result, around 6 million years ago, when the temperature reached a certain level, the formation of ocean currents such as the Gulf Stream began, which also play an important role in redistributing heat throughout the planet. Massive extinction of animals and plants in the Anthropocene is a phenomenon that is currently occurring at such a pace that many scientists consider it the sixth mass extinction on the planet. According to estimates, the rate of species disappearance today is tens and even hundreds of times higher than the natural background level of extinction, which, based on paleontological data, is approximately 1 species per million per year. Since the beginning of the 20th century and to this day, according to the International Union for Conservation of Nature, more than 1 million animal and plant species are at risk of extinction. The main causes of this are the destruction of natural habitats, climate change, pollution, and excessive resource exploitation. Meanwhile, humans have become the only species capable of so radically altering ecosystems, often without realizing the consequences of their actions. For example, deforestation in North and South America, as well as in Asia, leads to the disappearance not only of plants, but also of animals that depend on these ecosystems. In Brazil, according to the National Institute for Space Research, in 2021, more than 10,000 square kilometers of the Amazon rainforest were cleared, equivalent to the area of Switzerland. Climate change leads to the fact that many species cannot adapt to new conditions, which also contributes to their disappearance. An example of this is the change in temperature regimes, which leads to shifts in the habitats of animals, such as penguins in Antarctica, which face food shortages due to the melting of ice. Meanwhile, the pollution of oceans with plastic and chemical substances destroys marine ecosystems. According to the World Wildlife Fund, by 2030, there may be more plastic in the oceans than fish by weight. Humanity has become not just an observer, but an active participant in the ecological transformation that affects the entire planet. In this context, it is important to understand that each species disappears not in isolation, but within a complex network of ecosystem interactions, making the consequences even more unpredictable. The restoration of destroyed ecosystems takes time, and in most cases, they do not return to their original state. As practice shows, the restoration of coral reefs, for example, after their destruction, occurs very slowly and often leads to the creation of less diverse ecosystems. Scientific research shows that the restoration of ecosystems can take decades, if not centuries. The extinction of species in the Anthropocene is not just numbers and statistics. It is a profound transformation of the entire biosphere, which has long-term consequences for all living beings on Earth. It is important to note that the current situation is unique in that one species, Homo sapiens, is causing global ecological changes that affect not only other species, but also humans, their health, and future. According to estimates, by 2050, climate change may lead to a deterioration of living conditions for more than 1.5 billion people worldwide. The arrival of the first people on the Australian continent led to catastrophic consequences for the local megafauna, which was unique due to 1 million years of evolution in isolation. Giant marsupials like Diprotodon, the largest known marsupial mammal weighing up to a ton, and Megatherium, an enormous lizard up to 7 meters long, became victims of the new predator, humans. Research shows that the megafauna of Australia went extinct roughly between the 14th and 10th millennia before our era, coinciding with the arrival of the first humans, known as Aborigines, who hunted these giant animals. The isolation of Australian fauna made it particularly vulnerable to this new threat, as local species did not have an evolutionary history of dealing with predators like humans. The disappearance of large herbivores like Diprotodon and Procoptodon, as well as large predators, led to significant changes in the ecosystems of Australia. These giant herbivores played a key role in maintaining vegetation, and their absence led to changes in the composition of flora. Without large animals that consumed plants and maintained the balance of the ecosystem, some species began to dominate, contributing to changes in the plant cover of the continent. For example, forests became less diverse, and open spaces were filled with more drought-resistant plant species like eucalyptus. This, in turn, changed the fire regime, as drier and less diverse ecosystems became more susceptible to seasonal fires. Research shows that the frequency of forest fires increased, further altering the landscape of Australia. Scientific works, such as those by Professor Leon Brown, emphasize that changes in ecosystems also affected the extinction of some bird species, such as the giant emu, which could not adapt to the new conditions. As a result, the extinction of megafauna not only led to the disappearance of individual species, but also fundamentally altered the structure of ecosystems, with long-term consequences for all flora and fauna of Australia. Currently, archaeological findings show that megafauna, including giant kangaroos and giant lizards, has completely disappeared, leaving behind only fossils and traces in the form of ancient bones. The dodo, or dronte, was a unique flightless pigeon that inhabited the island of Mauritius. Its disappearance is one of the most tragic chapters in history. This species, which had no natural predators, could reach a height of 1 meter and weigh around 10 kilograms. In the 16th century, when Portuguese sailors first discovered the island, dodos freely roamed the shores, unafraid of humans. Their meat, tender and nourishing, attracted the attention of European colonizers. In the early 17th century, when the Dutch began colonizing Mauritius, they brought domestic animals such as pigs and dogs, which quickly became predators of the dodos. As a result, dodos became vulnerable, as they were unable to defend themselves against these new threats. In this context, the hunting of dodos became not just a matter of survival, but a genuine mass slaughter. By the 18th century, when the British took control of the island, the dodo was on the brink of extinction. According to zoologist and researcher John Gould, by the year 1800, only a few individuals remained. 8 years later, in 1818, the last dodo was sighted, and soon this species was declared extinct. It is quite symbolic that the dodo's disappearance occurred during an era when people did not yet understand the value of unique ecosystems and their inhabitants. The lack of awareness about the importance of preserving biodiversity led to this remarkable pigeon becoming a victim of human greed and negligence. Interestingly, in the remains of the dodo, fossils were found that show this species had no natural enemies, and its ecological niche was free. Deforestation for the construction of plantations also played a role in the dodo's extinction, as this species lived in tropical forests and depended on them. According to scientists, dodos were completely wiped out within less than 100 years, leaving behind only memories and ancient descriptions. Modern methods of preserving endangered species include a range of innovative approaches aimed at preventing further extinctions and restoring ecosystems. One of the most well-known is the captive breeding program, which is actively used to save species like the Amur tiger, which is on the brink of extinction due to hunting and habitat loss. In zoos around the world, including the Moscow Zoo, specialized programs have been created for the captive breeding of these tigers, with the goal of reintroducing them back into their natural habitat. For example, in 2000, Russia launched a reintroduction program for the Amur tiger, where 23 individuals were released into the wild, which positively impacted the population's numbers. Cryopreservation of genetic material is another crucial method for preserving biodiversity. This technology allows the preservation of DNA samples and reproductive cells of endangered species in a frozen state, enabling the possibility of restoring populations in the future. In the early 2000s, an international team of scientists from the USA and Japan developed a method for cryopreserving eggs and sperm of species like the black rhino, which allows the preservation of genetic diversity and, if necessary, the use of these materials for creating new generations through artificial insemination. Restoring ecosystems is the third aspect that is actively being researched and implemented by scientists and conservation organizations. In the early 2000s, Australia launched an initiative to restore the populations of endangered species such as the red fox, which was almost completely eradicated. Within this program, efforts are made to restore their natural habitats, including the restoration of plants and the creation of protective zones where these animals can live and breed without threats from predators and humans. In some cases, it has been shown that the restoration of even small areas of ecosystems can significantly impact the numbers of local populations, as demonstrated by the project for restoring wetlands on the eastern coast of the USA, where the restoration of the ecosystem led to a 50% increase in the numbers of rare bird species. Scientists are conducting active research and monitoring of the status of endangered species populations to track the effectiveness of conservation programs. For example, in 2020, Kenya implemented a satellite monitoring system to track the migrations of wild animals, which allows for more effective management of their protection. Additionally, international organizations such as the World Wildlife Fund are working on creating global networks of protected territories, which helps to preserve biological diversity and ensure protection for numerous species. Preserving biodiversity requires a comprehensive approach that includes both scientific and practical measures. In 2009, at a conference in Copenhagen, it was proposed to create international funds to support conservation programs, as many states cannot independently finance such projects. The success of such initiatives depends on the cooperation between governments, private foundations, and scientific institutions, making this task multi-level and complex. Scientific research shows that biodiversity decreases by 25% each year, which causes concern among scientists and the public. Therefore, modern methods of preservation have become not just important, but vital for future generations. It is worth noting that, according to UNEP estimates, there are more than 1.5 million known species of animals and plants in the world, and many of them are on the brink of extinction. Anthropogenic climate change refers to a process in which human activities significantly impact the Earth's climate system. The primary mechanism behind this change is the intensification of the greenhouse effect, caused by the increase in the concentration of carbon dioxide and other greenhouse gases in the atmosphere. According to the World Meteorological Organization, the level of carbon dioxide in the atmosphere in 2020 reached record levels, exceeding 450 parts per million. This increase is primarily due to the burning of fossil fuels such as coal, oil, and natural gas, as well as deforestation and agricultural activities. Each ton of carbon dioxide emitted into the atmosphere traps heat, leading to an increase in global temperature. Every year, we observe the Earth's average temperature rising, and this, in turn, triggers chain reactions in the climate system. For example, warming leads to the melting of glaciers and polar ice caps, adding more water to the oceans and releasing methane, a potent greenhouse gas that was previously trapped in permafrost. In 2015, scientists from the University of Alberta in Canada found that methane emissions from thawing permafrost are increasing 30% faster than expected. This creates a feedback loop where warming leads to additional greenhouse gas emissions, further exacerbating the warming. Concurrently, human activities affect natural climate processes, such as the water cycle, leading to more frequent and intense weather events, such as hurricanes, droughts, and floods. For instance, in 2016, Hurricane Matthew, which struck Haiti and the United States, was one of the most destructive in recent decades, and its devastating power was largely due to changes in ocean temperatures caused by global warming. This creates a sense of growing imbalance in the planet's climate system, where climate conditions become increasingly unpredictable and extreme. All these factors combined pose serious challenges that threaten not only ecosystems but also the very existence of life on the planet. In 2018, research conducted by scientists from the London Environment Research Institute showed that more than 50% of the world's population lives in conditions affected by climate change, necessitating immediate action to mitigate its impacts. The area and thickness of the ice cover in the Arctic Ocean are rapidly decreasing, as confirmed by satellite observations. According to the National Oceanic and Atmospheric Administration of the United States, the minimum area of sea ice in September has decreased by almost 80% since the 90s of the 20th century. In 2020, the ice cover reached an unprecedented low level of 3 million square kilometers, the lowest on record. This melting of ice creates a critical positive feedback loop. The white reflective surface that previously reflected solar energy back into the atmosphere is replaced by dark water that absorbs up to 90% of sunlight. This exacerbates warming, as the water surface heats up much faster than ice. Industrial research conducted in 2018 at the University of Alberta showed that a 1 degree Celsius increase in water temperature can lead to a 30% acceleration in ice melt. Local ecosystems, such as sea ice, are home to many species, including marine mammals like polar bears and seals, which depend on ice as their habitat and food source. The decrease in ice area led the Canadian government in 2016 to conduct a study that showed a 30% decline in marine mammal populations over the past 3 decades. Indigenous peoples, such as the Inuit, face serious consequences of climate change, as the melting of ice disrupts traditional hunting and fishing paths. A study conducted in Nunavut in 2000 found that 30% of Inuit reported that climate change negatively impacted their traditional way of life. The increase in open water also creates new conditions for shipping and resource extraction, further exacerbating the ecological situation. In 2019, a Norwegian oil company announced plans to begin oil drilling in the Arctic, which sparked mass protests from environmentalists and indigenous peoples. The opening of new maritime routes also threatens existing ecosystems, as increased ship traffic leads to pollution and disruption of the natural balance. It is predicted that by 2030, the area of sea ice may decrease by 80% if current trends continue. As a result, the Arctic is not only a barometer of climate change, but also a zone of conflicting interests, where the needs of industry and the rights of indigenous peoples collide. In July 2021, a group of Norwegian researchers discovered that in some areas of the Arctic, the ice thickness had decreased to 1 meter, while in the early 90s it exceeded 3 meters. The conditions for life in the Arctic are changing with each winter, and this change is happening before the eyes of the world. Glaciers in Greenland and Antarctica are undergoing dramatic changes that are becoming increasingly apparent. Over the past decades, scientists have documented the accelerated melting of these massive ice shields, a result of global warming. For instance, since the early 2000s, the rate of melting of Greenland's glaciers has increased by more than threefold. Between 2011 and 2017, according to NASA data, Greenland lost around 31 billion tons of ice annually, equivalent to a 1 millimeter rise in sea level. A similar situation is observed in Antarctica, where, according to research, ice streams such as the Thwaites Glacier have been moving faster, sometimes at speeds of up to 40 meters per year. This movement leads to the formation and carving of gigantic icebergs, which became noticeable in 2000 when an iceberg of around 32,000 square kilometers broke off from the Larsen B ice shelf. Scientists from the University of Sussex noted in 2018 that such events, like iceberg calving, are happening more frequently and rapidly, indicating a loss of stability in the ice shields. Melting ice leads to the formation of large lakes beneath the surface, further weakening the structure and accelerating the melting process. These lakes, as research has shown, can suddenly release their waters, causing powerful underwater currents that further increase the speed of glaciers moving towards the sea. As a result, Antarctic and Greenland glaciers are not only sources of new icebergs, but also significant factors in global sea level change. Estimates suggest that if all of Greenland's ice were to melt, sea levels could rise by 7 meters, threatening coastal cities worldwide. Research conducted in 2019 showed that over the past 30 years, the volume of ice in Antarctica has decreased by more than 300 billion tons per year. This slow but inexorable change in polar regions has global consequences, affecting climate systems, ecosystems, and sea levels worldwide. Furthermore, data presented in 2020 indicates that the melting of glaciers could alter ocean currents, impacting the climate in other parts of the world, including Europe and North America. These changes in polar regions underscore the urgent need to address issues related to climate change and its impacts. The rise in the level of the world ocean is due to two main factors: the melting of glaciers and the thermal expansion of water. According to the National Oceanic and Atmospheric Administration of the United States, the ocean level is rising at an average rate of 3 millimeters per year, and this process is accelerating with each decade. Glaciers, particularly those in Greenland and Antarctica, are losing ice at an alarming rate. Research conducted in 2020 showed that the rate of ice loss in Greenland over the past 18 years has increased by 300%. This makes low-lying coastal areas increasingly vulnerable. For instance, in Bangladesh, where a significant portion of the territory is located just a few meters above sea level, the effects of rising ocean levels are already evident. By the year 2030, the sea level is expected to rise by 1 meter, which could displace around 30 million people and cause severe infrastructure problems. Coastal cities such as New York, Mumbai, and Shanghai are facing the need to adapt their infrastructure to these new conditions. For example, after Hurricane Sandy in 2012, authorities in New York began work on projects to reinforce the shoreline and build protective barriers. Similarly, Mumbai, which already suffers from floods, plans to construct new drainage systems and improve existing ones. Island nations such as the Maldives and Tuvalu are on the brink of disappearance. According to the UN, Tuvalu may become uninhabitable by the year 2030, which is forcing the governments of these countries to consider population migration options. For example, the Maldives are discussing the possibility of relocating residents to higher islands in the Indian Ocean. This migration process has already begun. In 2018, several thousand residents of Kiribati started moving to New Zealand, marking the first step in the creation of climate refugees. The situation remains critical, and without measures to reduce carbon dioxide emissions and adapt cities to these changes, many coastal settlements may become uninhabitable. In the coming decades, the level of the world ocean could rise by 1 to 2 meters, threatening the existence of entire countries. Changes in precipitation patterns, driven by global warming, are becoming increasingly apparent and worrying. According to data from the Intergovernmental Panel on Climate Change, since the beginning of the 20th century, the global temperature of the Earth has risen by 1 degree Celsius, which has already affected the distribution of precipitation. In some regions, there is a sharp increase in the intensity and frequency of extreme weather events. For example, in the eastern part of Africa, where rain traditionally fell in March and April, there are now cases of severe flooding, especially in countries like Uganda and Kenya. In 2020, floods in Uganda destroyed more than 2,000 homes and resulted in the deaths of more than 100 people. At the same time, in the southwestern United States, particularly in California, there is a trend towards prolonged and intense droughts. Since the 20th century, the amount of precipitation in this region has decreased by 30%. And in 2021, California experienced one of the most severe droughts in the last 100 years, leading to water restrictions and the destruction of agricultural crops. In such conditions, traditional methods of agriculture, based on predictable rainy seasons, become ineffective. Farmers are forced to adapt to new realities, transitioning to sustainable methods such as drip irrigation and the use of drought-resistant crops. However, even these measures do not guarantee success, as the changing climate continues to threaten food security. In South Asia, for example, an increase in the frequency of monsoon rains leads to floods that destroy fields and roads. In 2021, floods in India submerged more than 30,000 hectares of agricultural land, resulting in significant losses. Meanwhile, in other parts of the world, such as Australia, dry conditions are becoming the norm, and in some regions of the country, the level of precipitation has decreased by 40%. These climate changes create a growing risk of a food crisis, as countries can no longer rely on familiar production and distribution schemes. In the face of instability and unpredictability of weather, adapting urban infrastructure becomes a top priority. Cities need to equip drainage systems capable of handling sudden downpours, as well as develop plans for water supply in drought conditions. For example, the city of Melbourne, in response to changing climate, implemented a program for collecting rainwater and using recycled water for irrigation. However, even such measures are not always able to prevent the consequences of climate change. In China, for example, in 2022, heavy rains caused floods that submerged more than 500,000 homes and led to the evacuation of almost 1 million people. These events demonstrate that changes in precipitation patterns are not just a problem for individual countries, but a global challenge requiring joint efforts. Ultimately, statistics indicate that by the end of the century, some regions may lose up to 7% of their gross domestic product due to the consequences of climate change and its impact on agriculture. Geoengineering represents a concept that involves deliberate intervention in Earth's climate system to mitigate the consequences of global warming. This approach emerged against the backdrop of growing recognition that traditional methods of combating climate change may be insufficient. In the early 21st century, when atmospheric carbon dioxide levels exceeded 400 parts per million, scientists began to consider active intervention as a means to lower the planet's temperature. The idea is to employ various methods to alter climate processes, such as increasing the reflectivity of the atmosphere or oceans and absorbing carbon dioxide from the atmosphere. However, these methods raise numerous questions and concerns. On one hand, inaction could lead to catastrophic outcomes, such as sea level rise, ecosystem destruction, and increased frequency of extreme weather events. On the other hand, intervention in natural processes carries risks associated with unpredictable consequences. Professor Kevin Anderson of the University of Manchester emphasizes that any intervention must be carefully considered, as results can be diverse and sometimes opposite to expectations. For example, changes in cloud cover can affect rainfall in different regions, leading to droughts in some areas and floods in others. This creates a complex ethical dilemma. Should we risk unpredictable consequences for the potential salvation of the planet? Research indicates that any attempts at geoengineering should be accompanied by broad public discussions, as the consequences of such decisions can affect not only current generations, but also future ones. Debates on geoengineering are becoming increasingly relevant, especially in light of the consequences of climate change already being felt in many parts of the world. According to the Intergovernmental Panel on Climate Change, if no serious measures are taken, by the end of the century, the planet's temperature could rise by more than 3 degrees Celsius, leading to irreversible impacts on ecosystems and human life. In this context, geoengineering appears as a potential tool, but one that requires a deep assessment of risks and consequences. In the 20th century, scientists began to realize that Earth's climate systems are complex and interconnected, making any intervention potentially dangerous. For instance, the Solar Radiation Management Project proposed artificially reducing solar radiation, but such actions could affect global weather conditions, impacting agriculture and water resources. Despite the widespread desire to address climate issues, approaches related to geoengineering require careful analysis, as the consequences could be far-reaching and unpredictable. These questions are already being discussed at international conferences, such as the UN Climate Conference, where countries discuss not only the need to reduce carbon emissions, but also the potential risks of geoengineering technologies. It is important to note that successful project implementation requires collaboration among scientists, governments, and the public to minimize risks and ensure that the technologies being deployed are safe. Modern research shows that without active human actions, humanity will not be able to avoid serious climate changes that could threaten not only ecosystems, but also the very existence of human civilization. In this context, the need for comprehensive and well-thought-out approaches to geoengineering is becoming increasingly evident. Spraying aerosols in the stratosphere is one of the most discussed geoengineering technologies aimed at reflecting solar radiation and temporarily reducing global temperature. This technique is based on simulating volcanic activity by releasing particles such as sulfur into the atmosphere, which form clouds that reflect sunlight. Studies show that if enough sulfur is sprayed at an altitude of around 24 kilometers, it could lower Earth's temperature by 1 to 2 degrees Celsius. There are various technical solutions for delivering these aerosols to the stratosphere. One method involves using high-altitude aircraft like the Global Hawk that can carry and spray materials at heights where they can effectively reflect solar radiation. Another approach involves using probes or even rockets to deliver aerosols to the upper layers of the atmosphere. These methods have been tested on a small scale, for example, in the year 2000, when aerosols were used to study their impact on the climate. However, such interventions have potential side effects. For instance, changes in precipitation patterns can lead to uneven distribution of rainfall, exacerbating droughts in some areas and floods in others. There is also concern that continuous spraying of aerosols could negatively affect the ozone layer, which protects Earth from ultraviolet radiation. A study conducted in 2009 showed that even small changes in ozone levels could increase cases of skin cancer and other diseases in humans. Since this technology still requires further research and discussion, it is important to consider that its use should be strictly regulated and controlled. Scientific communities, such as the Institute of Atmospheric Research in Essex, are actively studying the consequences of such measures and trying to determine how to minimize the risks associated with their use. In 2018, a group of scientists from Cambridge University proposed a model that takes into account climate change predictions when using aerosols, emphasizing the need for a comprehensive approach to this problem. Furthermore, in 2020, a study was published that considered possible scenarios related to the widespread use of this technology and found that, in case of failure, there could be serious climate consequences, such as changes in weather patterns. The development of effective and safe aerosol spraying technologies should be a priority for scientists and governments worldwide, especially in the face of the growing climate crisis. It is important to remember that even if aerosols can temporarily slow down warming, they do not address the fundamental issues such as greenhouse gas emissions. Ultimately, there are still many questions about the long-term effects of aerosol spraying, and further research is needed to understand all aspects of this technology. Technologies for capturing and storing carbon represent one of the most ambitious challenges on the path to minimizing the consequences of climate change. Direct capture of carbon dioxide from the atmosphere is becoming an essential element in the strategy to achieve carbon neutrality. A method known as direct air capture, DAC, allows for the extraction of CO2 from atmospheric air using various chemical processes. For example, the company Climeworks, founded in 2016 in Switzerland, has developed installations that can capture up to 1,000 tons of carbon dioxide per year. This is achieved using special filters that bind CO2 as air passes through them, and then CO2 is extracted using heat, which requires significant energy input. It is important to note that such technologies require the development of infrastructure comparable in scale to the oil industry, but working in the opposite direction. Instead of extracting carbon from the Earth's depths, systems must be created that will return it back. At present, the only solution for long-term storage of captured CO2 is its injection into underground geological formations, such as depleted oil and gas fields or salt domes. For instance, the Petronova project in Texas, launched in 2016, uses CO2 capture technologies to reduce CO2 emissions at a coal-fired power plant. This project allows for the capture of around 2 million tons of CO2 per year, which is then used to enhance oil recovery. The second main technology is biological carbon capture, which involves using plants to capture CO2 through photosynthesis. Research shows that forests like the Amazon rainforest can absorb around 2.5 billion tons of carbon dioxide per year, but their destruction negatively impacts this ability. To effectively capture carbon, a network of such projects needs to be created that operates on a global scale. This requires not only investment in scientific research, but also the development of policies and economic incentives to support these technologies. In 2020, the European Union presented a strategy aimed at reducing carbon emissions by 75% by 2030. This includes significant investments in carbon capture and storage technologies, underscoring the importance of this sector in combating climate change. The increasing levels of carbon dioxide in the atmosphere, which have reached over 400 parts per million, require urgent measures to prevent catastrophic climate changes. Carbon capture technologies can become a key tool in achieving these goals, but it is important to remember that they do not replace the need to reduce emissions at the source. In the context of traditional energy methods continuing to dominate, the significance of developing effective carbon capture methods becomes more pressing than ever. Forest restoration, wetland restoration, and marine ecosystem restoration represent natural solutions for carbon sequestration, capable of significantly reducing the level of carbon dioxide in the atmosphere. Forests, for instance, play a crucial role in the carbon cycle. 1 hectare of mature forest can absorb up to 20 tons of carbon per year. The greatest contributions to this are made by tree species such as sequoia and eucalyptus, which are characterized by their rapid growth and ability to accumulate carbon in their trunks, branches, and roots. Forest restoration, especially in tropical regions, can revive ecosystems that have been destroyed due to deforestation and agricultural production. According to the World Bank, restoring 30% of the cleared forests could help remove around 1 billion tons of carbon per year. Wetland restoration is also a vital aspect. Wetland ecosystems, such as peatlands, can retain carbon in their waterlogged soils. For example, in Europe, wetlands store nearly 200 billion tons of carbon, equivalent to more than 11 years' worth of carbon emissions from all the cars on the continent. Restoration of these ecosystems can be achieved through natural methods, such as restoring the water regime and creating protective zones. Marine ecosystems, such as mangrove forests and seagrass meadows, also serve as powerful carbon sinks. Mangrove trees can absorb up to 14 times more carbon than tropical forests, thanks to their ability to accumulate carbon in their underwater soils. It is estimated that restoring mangrove forests over an area of 3 million hectares can absorb around 1 billion tons of carbon over a decade. Healthy ecosystems not only sequester carbon, but also provide numerous other ecological services. For example, restored forests and wetlands contribute to biodiversity conservation, providing habitats for numerous plant and animal species. They also help regulate water flow, preventing floods and ensuring clean water. Restoration of marine ecosystems supports fisheries and protects coastlines from erosion. Coastal mangrove forests can reduce wave energy and protect coastal communities from destructive storms. Sustainable ecosystems, in general, have a higher capacity for carbon sequestration, making them an integral part of strategies to combat climate change. Research shows that loss of biodiversity can reduce the effectiveness of carbon sinks, underscoring the need for a comprehensive approach to environmental conservation and the restoration of natural resources. The development and implementation of ecosystem restoration programs are necessary not only for environmental reasons, but also for ensuring sustainable development and the well-being of the population. It is important to remember that each restored wetland or forest not only sequesters carbon, but also serves as a valuable resource for future generations. Ecosystem restoration can form the basis for future eco-friendly technologies and sustainable use of natural resources. Asteroid danger refers to the ongoing threat posed by celestial bodies that freely traverse the Earth's vicinity. Every day, Earth encounters numerous small meteoroids that burn up in the atmosphere, creating bright meteors known as shooting stars. However, within this cosmic ocean, there are also larger bodies, asteroids that can cross Earth's orbit. Approximately 30,000 known asteroids are within 1 astronomical unit of Earth, and some of them pose a potential threat. The sizes of these objects range from several meters to hundreds of kilometers in diameter. For instance, an asteroid with a diameter of 300 meters could cause catastrophic consequences upon impact, releasing an enormous amount of energy equivalent to the explosion of millions of tons of TNT. According to NASA data, there are roughly 8,000 objects in Earth's vicinity that are classified as potentially hazardous asteroids. These bodies move along orbits that intersect with Earth, and their trajectories are influenced by the gravity of other planets, which can lead to changes in their paths. Scientific research shows that asteroids not only pose a threat, but can also be a source of valuable resources. Some of them contain rare minerals and metals that could be used in future space exploration and even for technological development on Earth. From a temporal perspective, geological processes on Earth and asteroid impacts have played a crucial role in the planet's evolution. For example, the impact with an asteroid approximately 66 million years ago is believed to have been one of the causes of the mass extinction of dinosaurs. This event led to changes in climate and ecosystems, opening the door for the evolution of new species. Our planet continuously moves around the Sun at a speed of around 100,000 kilometers per hour, and in this motion, it traverses zones filled with cosmic debris and potentially hazardous objects. Despite the development of various programs for tracking and detecting asteroids, many of them remain undetected until they approach Earth. Current observation methods can detect objects smaller than 100 meters, but not all asteroids can be identified. It is important to note that in case of detecting a threatening object, the reaction time may be extremely limited. Scientists continue to study the orbits of known asteroids to predict their potential collisions with Earth. The cosmos is not empty, but a dynamic environment filled with moving objects that constantly change their positions. In such a cosmic environment, Earth is just one of many planets, and our existence is always influenced by these celestial bodies. Astronomical research indicates that in the future, humanity may face new challenges related to asteroids, and it is important to be prepared for this. Therefore, the study of asteroid danger remains an important task for science and society, emphasizing the need for the development of technologies to protect against potential threats. According to estimates, the probability of Earth colliding with an asteroid larger than 100 meters in the next 100 years is approximately 1 in 1,000. However, considering the scale of the cosmos and the number of objects in it, this may seem insignificant. Scientific research and technologies, such as asteroid tracking programs, play a crucial role in minimizing this threat and ensuring the safety of our planet. Astronomers worldwide employ a range of advanced technologies to detect and catalog near-Earth objects, such as asteroids and comets. To achieve this, they use powerful telescopes, for example, the Palomar Observatory in California, which houses a 1-meter telescope. With this, astronomers can observe the sky and record moving objects. Additionally, the Pan-STARRS, Panoramic Survey Telescope and Rapid Response System, project on the Hawaiian Islands, uses automated systems for rapid sky scanning and the detection of objects as small as several tens of meters. This observatory began its operations in 2012 and has discovered thousands of new asteroids in a short period. Methodical sky scanning involves the use of algorithms that analyze images obtained by telescopes and identify objects changing their position relative to the stellar background. These algorithms can process vast amounts of data and highlight movements that may indicate the presence of a near-Earth asteroid. After detection, astronomers calculate the orbits of these objects using a trajectory method based on observations over several nights. Based on these calculations, astronomers can predict how close an object will approach Earth in the future. A crucial aspect is assessing the potential danger of each detected object. For this, the Torino scale is used, which classifies asteroids based on their size, orbit, and probability of impact with Earth. For example, an asteroid that could cause significant damage upon impact receives a high rating, while smaller and safer objects receive lower scores. International cooperation is also essential, such as the NEOWISE program launched by NASA, which uses a satellite to detect and monitor near-Earth objects. Launched in 2009, the satellite has an infrared camera and can detect objects that are difficult to see in visible light. Within this program, over 30,000 objects have been discovered. Additionally, ESA's Space Debris Office focuses on tracking space debris and near-Earth objects, highlighting the importance of collaborative efforts in space security. Concurrently, numerous research groups and universities worldwide, such as MIT and CALTECH, are developing new algorithms and models to enhance prediction accuracy and reduce the risk of impact. Astronomers also collaborate with the Minor Planet Center, which maintains a comprehensive database of all known near-Earth objects, enabling rapid access to information about them. As of 2020, the database contained over 35,000 registered objects, and this number continues to grow. Kinetic impactors represent one of the most discussed methods for protecting Earth from asteroid threats. This concept involves launching specialized spacecraft that will collide with an asteroid to alter its trajectory. For example, NASA is developing a mission called DART, which is scheduled to be launched in 2021. The goal of this mission is to collide with the asteroid Dimorphos, which is a satellite of the asteroid Didymos. It is expected that such an impact will change the orbit of Dimorphos, allowing researchers to assess the effectiveness of this technology. Kinetic impactors could become the primary tool in humanity's arsenal for preventing potential collisions with large celestial bodies. Another approach to planetary defense involves gravitational tugboats, which use the gravity of a spacecraft to gradually alter the orbit of an asteroid. This idea is based on the principle that even a small influence over an extended period can result in significant changes. In 2017, a group of scientists from the European Space Agency presented a concept for a gravitational tugboat that could be launched towards an asteroid to gradually change its trajectory. If the spacecraft remained near the asteroid for several years, its gravitational field could alter the body's course, preventing a collision with Earth. Nuclear explosions are also considered as a potential means of asteroid defense. This method involves detonating a nuclear device near an asteroid to either destroy it or alter its trajectory. In 2015, scientists from the University of Texas presented research showing that nuclear explosions could be effective against asteroids up to 400 meters in diameter. Such an approach requires careful planning to avoid fragmenting the asteroid into dangerous debris. The effectiveness of nuclear explosions depends on their precision, which requires extensive work and thorough preparation from scientists. Recognizing the real threat posed by asteroids, humanity is actively developing technologies that can change the situation. This is not just about protection, but also about transforming from a passive victim to an active participant in shaping a safe near-Earth environment. The Planetary Defense Project aims not only to study asteroids, but also to develop strategies for preventing them. As of 2020, more than 30 experiments have been conducted within this project to model the effects of various methods on asteroids. The use of new technologies and approaches significantly increases the chances of protecting our planet from potential cosmic threats. Scientific research and international cooperation are becoming crucial aspects of this work. In 2018, more than 50 countries signed an agreement on joint protection against asteroid threats, demonstrating global awareness of the problem. This cooperation includes data exchange, joint missions, and the development of technologies aimed at protecting the planet. For example, in 2019, an international conference was held in Italy where scientists discussed the prospects of creating a global system for monitoring near-Earth objects. As a result, it was proposed to establish a unified center that would coordinate efforts from all countries in the area of space threat protection. Thus, humanity is actively working to not only predict but also prevent potential catastrophes, which is a significant step towards creating a safe near-Earth environment. All these efforts confirm that we are capable of dealing with cosmic threats if we act together and use all available technologies. In 2020, NASA launched the LUCY mission, which is studying Jupiter's Trojan asteroids to better understand their composition and potential threats. International cooperation in the field of planetary defense is gaining increasing importance, uniting countries in the face of threats emanating from space. In 2018, within the framework of the United Nations, the Planetary Defense Group was established, which coordinates the efforts of various states in monitoring potentially hazardous objects. This group includes participants such as NASA, the European Space Agency, ESA, and the Russian space corporation, Roscosmos. Regular data exchange on observations has become a standard practice, enabling countries to jointly analyze information about the trajectories of asteroids and meteoroids that pose a threat to Earth. For example, in 2020, an international team of astronomers from the United States, Europe, and Japan jointly tracked an asteroid named 2019 VE7, which was then only 6 million kilometers away from our planet. This cooperation illustrates how a cosmic threat unites peoples, requiring the overcoming of political differences for the common safety of all Earth's inhabitants. In response to the growing threats, in 2020, cooperation between NASA and ESA was initiated for the development of a joint mission to study and deflect asteroids, known as AIDA, Asteroid Impact and Deflection Assessment. This program includes 2 key stages. The first is the launch of NASA's DART probe to collide with the asteroid Didymos to change its trajectory, and the second is the launch of ESA's Hera probe to study the effects of the collision in 2023. These missions demonstrate that planetary defense requires not only scientific but also political efforts, as successful project implementation requires coordinated actions and funding from several countries. Additionally, in 2020, the first International Conference on Planetary Defense was held, where over 100 representatives from different countries gathered to discuss methods of information exchange and joint actions in case of the discovery of a potentially hazardous object. These events highlight that international cooperation in the field of planetary defense is becoming not only a necessity, but also a foundation for building a safer future for all on Earth. The unification of efforts allows countries to share not only data, but also technologies, leading to the creation of a unified platform for responding to cosmic threats. As a result, astronomers and engineers from around the world are working on developing new methods of detection and tracking of objects that could potentially threaten our planet. For example, in 2021, a team of scientists from different countries jointly developed an algorithm that allows real-time analysis of data on the movement of asteroids and predicts their trajectories with high accuracy. This cooperation demonstrates how cosmic threats serve as a stimulus for the unification of human efforts, creating a platform for joint actions that could save millions of lives. Through tens of millions of years, the movement of tectonic plates will lead to the formation of a new supercontinent, which will be the result of continuous interaction between Earth's tectonics. Currently, the plates move at a speed of about 2 to 3 centimeters per year, which may seem insignificant. But in the scale of geological time, this is colossal distances. For example, in the past, there were supercontinents such as Pangaea, which formed around 300 million years ago and broke apart approximately 180 million years ago. This process has not stopped, and according to scientists, in the future we will witness a new unification of continents. Thus, according to geologists, in the next supercontinent that will arise, the continents may merge into a single whole, which in turn will change the climatic conditions and ecosystems on Earth. It is predicted that the new continents will be located closer to the equator, leading to a warmer climate and changes in familiar natural landscapes. Scientific research shows that in 12 million years, the Indian plate will continue its movement northwards and collide with the Eurasian plate, leading to further uplift of the Himalayas. At the same time, the African plate will move northwards, approaching Eurasia, which will create new geological structures and potentially change the distribution of resources, such as minerals. Similarly, the movement of the Pacific plate will continue, leading to the formation of new volcanoes and earthquakes in the region of fire. These changes will occur over millions of years, and humanity, like other organisms, will change or disappear as a result of these processes. From the perspective of time, the entire history of Earth is a continuous process of change and adaptation in response to tectonic movements. For example, as a result of the collision of plates, such as in the region of the fire ring, new mountain ranges are formed, which can cause landslides and changes in river courses. This leads to changes in ecosystems, and animal and plant species are forced to adapt to new conditions or go extinct. Geological processes do not stop, regardless of whether humanity exists or not. Even if we look at the history of Earth, we will see that over the last 500 million years, there have been 5 mass extinctions, each of which was caused by significant geological changes. For example, at the end of the Permian period, a mass extinction occurred that destroyed around 90% of all species on the planet, and this was related to volcanic activity that led to changes in the atmosphere and climate. Comparing this with today, it can be said that new supercontinents will form, regardless of human efforts to prevent climate change or preserve ecosystems. Earth continues its cycle, and it will not stop as long as there are tectonic plates moving, colliding, and forming new structures. This movement of plates is the basis of geological activity, which will continue, forming new lands and changing old ones, and eventually, when we look at our planet through tens of millions of years, it will look completely different. In the end, even if humanity disappears, Earth will continue to evolve, creating new continents that will be inhabited by completely different forms of life, adapted to new conditions. In this context, it is important to note that geological processes are not something static. They are dynamic and constantly changing, creating new conditions for life. Scientific research shows that as a result of these processes, a new supercontinent may arise in approximately 30 to 40 million years. Specialists suggest that in approximately 250 million years, the continents will reunite, forming a new supercontinent known as Pangaea Ultima. This model was proposed in 2013 by a group of geologists, including Professor Tim Fitzpatrick from the Australian National University, who studied plate tectonics and global climate changes. According to the calculations of scientists, Pangaea Ultima will take the form of a vast landmass located around the equator, with massive mountain ranges formed as a result of the collision of tectonic plates. According to the forecasts, the central regions of the supercontinent will be located at an altitude of more than 2.5 kilometers above sea level, creating extremely continental conditions with high temperatures and low humidity. At the same time, the coasts of Pangaea Ultima will have a milder climate due to the influence of the oceans that will surround this landmass. In particular, on the eastern coast of the new continent, there may be tropical conditions conducive to the formation of extensive jungles, while on the west, more arid regions resembling modern deserts may arise. It is expected that the new landform will have a length of more than 7,000 kilometers and a width of around 4,000, comparable to the sizes of modern continents. Scientific research shows that this supercontinent will exist for several tens of millions of years before a new cyclic process of plate breakup and displacement begins. Thus, Pangaea Ultima will become home to numerous new ecosystems and possibly even new life forms adapted to the unique climatic conditions. A notable feature will be the absence of oceans as we know them today, which will lead to significant changes in precipitation cycles and temperature regimes. It is expected that in the center of the supercontinent, a massive internal ocean will form, serving as a source of moisture for the surrounding territories. As the climate changes in this region, significant changes in the biosphere may occur, as new conditions will lead to evolutionary changes in existing species and the emergence of new ones. Research shows that such processes have occurred in the past when supercontinents such as Gondwana and Pangaea formed, as evidenced by the discovery of fossil remains in different parts of the world. Scientific models demonstrate that in the conditions of Pangaea Ultima, meteorological conditions will be significantly different from the present, opening new horizons for the study of climate changes and biological adaptation. In the supercontinent of the future, extreme climatic conditions are expected to alter the familiar face of Earth. According to climate experts, such conditions could arise in 250 million years, when the supercontinent reaches its maximum form. The interior regions of this vast landmass will experience sharp seasonal temperature fluctuations, with summer temperatures potentially reaching up to 100 degrees Fahrenheit and winter temperatures dropping to 0 degrees Fahrenheit. These temperature swings will create harsh conditions for life, limiting the existence of complex biota. In such conditions, where aridity becomes the norm, the interior lands will transform into deserts similar to today's Sahara or Kalahari, with rare oases where life may persist. Meanwhile, the coasts of the supercontinent will have a monsoon climate, providing abundant rainfall during certain seasons and creating unique ecosystems along the coastal line. These monsoon rains could reach 2,000 millimeters per year, significantly exceeding current averages for such regions. Thus, biodiversity will be concentrated in these coastal zones, where tropical forests and mangrove swamps will serve as sanctuaries for numerous species. Such a climate will create conditions where most of the land will be largely uninhabitable, and ecosystems will adapt to new challenges, while coastal species will exhibit high diversity and complexity. In these coastal ecosystems, new plant species with adaptive mechanisms to survive in conditions of increased salinity and frequent flooding may emerge. These changes could lead to the formation of unique ecosystems that differ significantly from those we know today, potentially giving rise to new predators and herbivores adapted to conditions we cannot even imagine. As a result, life forms will become more specialized, and new food chains will develop, dependent on these specific ecosystems. The biodiversity concentrated in coastal zones will be crucial for maintaining ecosystems on the supercontinent, while the interior regions will remain virtually uninhabited, creating a unique contrast between desert and wet regions. Such changes in climate and ecosystems could be key factors in the study of organism adaptations and the dynamics of ecosystems, which in turn will help in understanding biological processes that have occurred on Earth over millions of years. In the future, millions of years after the disappearance of humanity, life on Earth will continue to evolve, adapting to new conditions shaped by changing climate and ecosystems. As sea levels rise, coastal zones will expand, while inland areas will become less habitable, leading to the formation of unique ecosystems at the interface between sea and land. In such conditions, new groups of organisms may emerge, occupying ecological niches left vacant by the disappearance of humans. For example, some marine mammals, such as dolphins, may evolve into larger and more adapted forms, capable of deeper diving and improved echolocation for hunting fish in murky waters. Research indicates that in conditions of increased water temperature, many coral species may develop symbiotic relationships with new microorganisms, ensuring the survival and prosperity of coral reefs, which will become key ecosystems for marine life. Meanwhile, on land, in the absence of humans, new mammals may appear, filling the niches left behind. For instance, rodents may evolve into larger creatures, similar to modern pigs, with unique traits enabling them to survive in changing climates. Additionally, with the expansion of forests, new tree species with unique adaptations to arid conditions may emerge, such as trees with deeper roots capable of extracting water from underground layers. Microorganisms also play a crucial role in this process. Some may develop new ways of processing toxic substances released during natural catastrophes, such as volcanic eruptions. In conditions where deserts cover a significant portion of the land, organisms capable of photosynthesis using the heat of the earth instead of sunlight may arise, allowing them to survive in extreme conditions. These organisms could form the basis for new ecosystems as the biosphere slowly but inevitably recovers. It is not unlikely that in such an environment, complex forms of life, including multicellular organisms, may develop, exhibiting entirely different ways of interacting with their surroundings compared to modern animals and plants. As a result, life on Earth, millions of years after the disappearance of humanity, may take forms that are currently difficult to imagine. Such changes may occur at relatively rapid rates, as natural selection will act on new organisms, ensuring their survival and reproduction in conditions vastly different from those that exist today. For example, in conditions of increased radiation caused by atmospheric changes, organisms with protective mechanisms similar to those observed in some exotic marine organisms capable of surviving in radiologically contaminated waters may emerge. This evolution may take millions of years, but ultimately, it will lead to the creation of ecosystems that are completely new and unique. It is expected that in such conditions, life will develop towards greater complexity and diversity than we can currently imagine. Consequently, millions of years after the disappearance of humanity, Earth will be home to diverse forms of life that will undergo changes in response to new conditions, creating ecosystems teeming with unexpected interactions and adaptations that may even surprise the most experienced researchers. Studying the distant future of Earth, it is impossible not to ponder how it will change under the influence of numerous factors acting over billions of years. Internal processes such as plate tectonics will continue to shape the planet's landscape. Plates moving at a speed of several centimeters per year will create new mountain ranges and faults, similar to how the Himalayas continue to grow due to the collision of the Indian and Eurasian plates. Oceans, which currently cover more than 70% of Earth's surface, may change due to sea level rise caused by the melting of polar ice and thermal expansion of water, leading to the flooding of coastal areas. External factors such as solar activity and asteroid impacts will also influence the climate and geological activity. Gradually increasing solar brightness will eventually intensify the greenhouse effect and change the climate, making the planet less habitable as we know it. As a result, flora and fauna will adapt to new conditions, as has happened in Earth's history when dinosaurs disappeared and mammals took their place. Ice ages and warm periods, such as the Pleistocene, when large parts of North America and Europe were covered by ice, will recur, leading to significant changes in ecosystems. Examples of such changes can be seen in Earth's history, such as the transition to a warmer climate around 35 million years ago due to changes in the planet's orbit and tilt. Against this backdrop, tectonic processes will continue to create new continents, which may unite into supercontinents, as happened with Pangaea, which existed around 300 million years ago. Thus, over billions of years, Earth will go through numerous cycles that will shape its appearance, like a potter shaping clay. The impact of volcanic activity, similar to that which occurred during the Triassic period when giant volcanoes erupted, filling the atmosphere with carbon dioxide, will make its own adjustments to the climate, creating conditions for the formation of new ecosystems. On the horizon, new species may emerge, evolving in conditions vastly different from those that existed during the human era. Ultimately, all this will create a unique biospheric balance that will differ from our time. Studying these processes, it is worth remembering that Earth as a planet has existed for more than 4.5 billion years, and during this time, it has experienced numerous catastrophes, including mass extinctions, such as the event around 60 million years ago when an asteroid that struck the territory of present-day Mexico caused the extinction of dinosaurs. The process of changing Earth will continue, and what we currently consider normal will become just a small episode in its endless history. The sun, throughout its existence, has been gradually increasing its brightness, which inevitably affects the climate of Earth. Today, it shines approximately 80% brighter than it did when it was formed about 4.5 billion years ago. As a result of this increase in solar radiation, the temperature on the surface of our planet is constantly rising. Scientists' predictions are based on models that show that in 300 million years, the sun's brightness will increase by about 10%. This, in turn, will lead to an increase in the average temperature on Earth by several degrees, which will be sufficient to cause significant changes in ecosystems. In particular, many plant and animal species will not be able to adapt to the new conditions and will begin to go extinct. With the increase in temperature, oceans will heat up, leading to their evaporation. Scientists suggest that in 500 million years, the sea level may decrease by hundreds of meters, as a significant portion of the water will simply turn into steam. This process will cause the biosphere to shrink, retreating to the poles, where the temperature remains relatively low. There are indications that in a distant future, approximately 1 billion years from now, Earth will become too hot for the existence of complex life forms. According to research conducted by scientists from NASA, by this time, the oceans may completely evaporate, leaving only desert landscapes that are unable to support life. There is concern that in the conditions of strong heat, the atmosphere will lose its components, and there will be no oxygen, which creates conditions for life as we know it. The process will be continuous, and in the end, the planet will become similar to Venus with its harsh conditions and high temperature, reaching more than 400 degrees Celsius. Scientists believe that it is precisely due to the increase in the sun's brightness in the distant future that Earth may lose all signs of life that we know today. Specialists in climate and astronomy continue to study this issue to understand how exactly the climate will change and which forms of life will be able to survive in these conditions. An important aspect is that the change in solar activity occurs unevenly, and over the course of hundreds of millions of years, there may be periods of both warming and cooling. But in the long term, the sun's brightness will only increase. When the Earth cools and active plate tectonics cease, the planet will become geologically dead. The essence of this process lies in the fact that the internal heat of the Earth, which currently sustains convective flows in the mantle, will gradually dissipate. These flows, which are the primary drivers of tectonic processes, will weaken, and as a result, the movement of continents will slow down and eventually stop. According to geologists' estimates, it will take about 1 billion years for the internal heat of the Earth to decrease to such levels that tectonic plates will no longer interact with each other. As a consequence, active volcanic activity will cease, which currently creates new mountain ranges and renews the Earth's crust. Without volcanoes like the currently active Kilimanjaro or Eiffel, sources of magma will disappear, leading to the extinction of many geological processes necessary for maintaining a dynamic planetary surface. Erosion, acting in the absence of new formations, will become the primary process shaping the landscape. It will gradually smooth out mountains, turning them into hills and then into plains. For example, if we take the Appalachian Mountains, which are already heavily eroded, they could turn into almost imperceptible elevations over millions of years, with rivers flowing down their slopes, leaving only insignificant traces of their existence. In the absence of tectonic activity and volcanic processes, the cycle of elements necessary for supporting complex life will be disrupted. Carbon, which is vital for all life, will no longer be recycled due to volcanic activity. The carbon cycle, which is currently regenerated through volcanic activity, will lead to a significant reduction in the amount of available carbon in the atmosphere and soil. Life, which requires a constant cycle of elements such as carbon, nitrogen, and oxygen, will be significantly limited. Additionally, the absence of tectonic activity will affect the climate. Without the movement of continents and changes in geographical conditions, there will be no new climatic zones, and existing climatic systems will become more static and predictable. Analyzing climate data, scientists suggest that in several billion years, Earth may become similar to Venus, a hot and waterless planet where life cannot survive. Ultimately, if we consider Earth over billions of years, we can see that it will become a lifeless body, where erosion and aging will replace all the dynamic processes we see today. Like the sunset over the ocean, which leaves no hope for tomorrow, Earth, devoid of its tectonic activity, will gradually lose its last signs of life. In 5 to 7 billion years, the sun will enter its final stage of life, transforming into a red giant. At this stage, its core will begin to contract under the influence of gravity, causing the temperature to rise to over 15 million degrees Celsius. This will lead to the sun starting to burn helium, which was formed as a result of hydrogen fusion. As a result of this process, the outer layers of the star will begin to expand, making the sun so large that its radius will exceed the orbit of Earth, engulfing Mercury and Venus. The situation for Earth will become critical. The temperature on the planet's surface will rise to thousands of degrees Celsius, and the atmosphere will begin to actively evaporate. Oceans, once teeming with life, will turn into steam, and the land will be covered with a scorching crust. At this moment, Earth will be a dead planet, subject to intense ultraviolet radiation and radiation from the expanded sun. The landscape will resemble an apocalypse. A scorched surface, once a home to millions of species, will be illuminated by a giant red sun disk occupying a large part of the sky. This radiant giant will be both terrifying and magnificent, like a colossal fiery sphere consuming everything in its path. In its final days, the sun will shed its outer layers, forming a planetary nebula, and the remaining core will become a white dwarf, gradually cooling and fading. The process of the sun becoming a red giant is nothing more than a grand finale that both illuminates and destroys. This fate awaits not only Earth, but the entire solar system, which will be in a state of complete chaos and irreversible changes. The situation underscores the fragility of the existence of planets and stars, as well as the constancy of cosmic cycles that have continued for billions of years. As the sun expands, its atmosphere will become so dense that it will cause even more heating and accelerated evaporation of water resources, depriving Earth of any chance of survival. By the end of this process, only a lifeless space will remain where life once raged, and the red giant will continue its journey through the vast expanses of the universe. The geological heritage of Earth is an invaluable chronicle, preserved in the layers of rocks that have formed over billions of years. These rocks, like the pages of a vast book, contain information about catastrophes, climate changes, and the evolution of life on our planet. For instance, sedimentary rocks can contain remnants of ancient organisms that lived millions of years ago, allowing researchers to reconstruct the picture of biological diversity and ecosystems of that time. Geologists, such as Dr. John L. Murphy, who conducted research in the field of paleontology, assert that studying these sediments allows us not only to understand how species lived and went extinct, but also how climate conditions changed. Stratigraphy, the science of rock layers, enables scientists to determine the age of various geological formations using radiometric dating methods. For example, carbon dating can help determine the age of organic materials preserved in sediments up to 150,000 years old. These layers can also contain traces of catastrophic events, such as volcanic eruptions or meteorite impacts, which left noticeable marks in the geological record. Impact craters formed as a result of asteroid collisions retain information about the consequences of these catastrophes, which could have led to mass extinctions, as was the case during the Permian extinction, when over 95% of all species disappeared. These data, recorded in rocks, allow us to study how Earth recovered from such catastrophes and what new forms of life emerged as a result. For example, studying rocks formed after the consequences of a meteorite impact in the modern Yucatan region has led to discoveries about how ecosystems quickly recovered and which species began to dominate in new conditions. The geological heritage of Earth not only helps us understand the past, but also predicts the future of our planet. Research conducted by scientists such as Dr. Elizabeth Hay shows that studying climate changes recorded in glaciers and sedimentary layers can provide insights into contemporary climate changes and their consequences. As a result, each layer of rock is not just a stone, but a page in a book that tells the story of how life on Earth adapted and survived in response to environmental changes. For instance, in some geological formations, one can see clear lines indicating the alternation of climatic periods, such as ice ages that occurred every 100,000 years. These lines, formed by sediments, are evidence of cyclical changes that occur on the planet. Earth itself is an archive that holds information about billions of years of evolution, where each rock, each crack, and each mineral tells its own story. Scientific research shows that understanding the geological heritage is not only important for science, but also for society as a whole, as it allows us to predict and minimize risks associated with natural disasters. For example, geologists use data on past earthquakes to assess the likelihood of future events and develop strategies to mitigate their consequences. The geological record of Earth, accessible for study, helps us realize that we live on a planet whose history is filled with events that shaped not only its surface, but also all life on it. With each new discovery, we gain more information about how billions of years of planet formation continue to influence the present. Each new layer of rock is not just the result of geological processes, but a testament to how Earth adapted to changes that occurred throughout its history. For example, data obtained from studying volcanic activity show that in the last millions of years, volcanoes not only shaped the landscape, but also influenced the climate. By studying phenomena such as lava flows and ash deposits, scientists can reconstruct the picture of how volcanic activity could change climatic conditions, which in turn influence the development of life. The geological heritage is a complex, multifaceted process that continues today, making each geological layer a valuable source of information about our planet. Analysis of isotopes is one of the most powerful tools in the hands of scientists, enabling them to reconstruct events that occurred millions of years ago. For instance, by studying the ratio of oxygen isotopes in ice cores obtained from Antarctica, it is possible to determine how the planet's temperature has changed over the past 100,000 years. In particular, data collected by an international team of scientists showed that during the last glacial maximum, the Earth's temperature was 8 degrees lower than it is now. Paleontological data further enrich this picture, allowing us to understand which animals and plants inhabited the Earth at that time and how they responded to climate changes. For example, fossil finds of dinosaurs from the late Cretaceous period in North America indicate that the climate was warm and humid, fostering the development of diverse ecosystems. Geophysical studies, such as seismic sounding, enable the study of Earth's internal structure and the identification of traces of ancient catastrophes, such as earthquakes and volcanic eruptions. In December 2008, Japanese scientists used seismic tomography methods to study the deep layers of the mantle beneath the Sakurajima volcano and discovered a large magma reservoir that could trigger powerful eruptions in the future. With the help of radiocarbon dating, developed in the mid-20th century, scientists can accurately date organic materials, allowing them to establish the chronology of events. For example, in 2014, a group of researchers used radiocarbon dating to date the remains of ancient marine mammals found on the coast of California and determined that they lived around 7,000 years ago, coinciding with a period of significant sea level changes. The combination of all these methods allows for a comprehensive reconstruction of ancient catastrophes, such as mass extinctions caused by asteroid impacts or volcanic activity. In this context, it is worth noting that the study of fossils found in a layer dating back to around 66 million years ago revealed a sharp decrease in species diversity as a result of an asteroid impact in the vicinity of present-day Yucatan, leading to the extinction of approximately 70% of all species on the planet. Modern technologies, such as computer modeling, help scientists simulate the consequences of these catastrophes and understand their impact on the development of life on Earth. For example, in 2009, a team of scientists from Harvard University created a computer model that showed how changes in climate due to volcanic activity could have caused mass extinctions at the end of the Permian period, when around 90% of all species disappeared. Thus, methods of isotope analysis, paleontological data, and geophysical research, combined with modern technologies, enable scientists to reconstruct not only the climatic conditions, but also the biological diversity that existed on Earth millions of years ago. The study of geological catastrophes provides valuable lessons for understanding contemporary processes and predicting future events. For instance, the investigation of the consequences of the 1883 eruption of Krakatoa demonstrates how a single catastrophic event can alter climatic conditions on the planet. As a result of the eruption, which released a vast amount of ash and sulfur into the atmosphere, the Earth's temperature dropped by nearly 1 degree Celsius over several years, affecting agriculture and ecosystems worldwide. Geologists like Dr. David Patterson analyzed the deposits left by such catastrophes to determine the temporal scales and impacts of these events. Their research shows that Earth has experienced not just one, but many such catastrophes, including mass extinctions and changes in ecosystems that have shaped our planet. For example, in 1991, Japanese scientists led by Professor Hiroshi Kawasaki discovered that the impact of an asteroid at the boundary of the Cretaceous and Paleogene periods, approximately 66 million years ago, resulted in the extinction of about 75% of all species on Earth, including dinosaurs. These catastrophes not only destroyed existing flora and fauna, but also created new ecological niches for other species. By analyzing geological layers and fossils, scientists can understand how organisms adapted to changing conditions and how new ecosystems emerged. For example, after the extinction of dinosaurs, mammals began to dominate the planet, ultimately leading to the emergence of humans. Such data help predict how contemporary climate changes may affect biological diversity and ecosystems. In recent decades, scientists have observed an increase in the frequency and intensity of natural disasters, such as hurricanes and floods, which requires a deeper understanding of the mechanisms behind these phenomena. Research conducted by a group of scientists led by Dr. Emma Griffiths shows that global warming can lead to more destructive hurricanes, a trend already observed in the Atlantic Ocean. Restoring historical data on catastrophes such as floods and earthquakes can help in developing adaptation and mitigation strategies. For instance, following a severe earthquake in Turkey in 1999 that claimed more than 7,000 lives, the country began implementing stricter building codes based on historical data on seismic activity. This approach not only minimizes damage but also saves lives. Knowledge of the past is key to understanding the present, and historical data on catastrophes teach us humility in the face of nature's forces, emphasizing the importance of readiness and adaptation to possible future changes. For example, research on the structure of glaciers in Greenland and Antarctica shows that ice melt is accelerating, which could lead to a rise in sea level by several meters in the next 100 years. These facts underscore the need for a serious approach to climate change and its consequences. Geological catastrophes such as meteorite impacts, volcanic eruptions, and earthquakes not only alter the landscape of Earth, but also leave a profound mark on human philosophical perception. For instance, in 65 BC, when one of the largest volcanic eruptions occurred on the territory of modern Iceland, it caused climate change in Europe and Asia, leading to famine and mass migrations. This event serves as a reminder of how fragile life on the planet is and how insignificant it is in the face of natural forces. Understanding that human history is intertwined with catastrophes makes us reflect on our place in the universe. Humanity, as a species, emerged as a result of complex interactions between evolution and random events, such as cosmic occurrences. For example, around 60 million years ago, after a meteorite impact that led to the extinction of dinosaurs, mammals were able to occupy the vacant niches and begin their development. This underscores that progress is not linear and predictable. It often depends on random and catastrophic events. Scientific research shows that approximately 99% of all species that ever existed on Earth have gone extinct, indicating that life is constantly at risk of disappearing. Philosophers like Albert Camus noted that the awareness of the absurdity of existence, when life can be cut short at any moment, gives it special value. This awareness of the catastrophic element in our history changes our understanding of progress. It becomes not just a result of evolution, but a product of struggle for survival in conditions of uncertainty. We live in an era where climate change, caused by human activity, is becoming a new geological catastrophe, emphasizing the need for adaptation and constant re-evaluation of our place in the ecosystem. The perception of the fragility of life in the face of natural forces not only shapes philosophical views, but also influences practical decisions we make. For example, research shows that more than 70% of the world's population lives in areas prone to natural disasters, requiring not just understanding, but active preparation for possible crises. Thus, awareness of geological catastrophes and their consequences becomes an important aspect of our lives, making us think more deeply about our place and role in this ever-changing world. Every geological event on Earth, from catastrophic volcanic eruptions to devastating earthquakes, not only causes destruction, but also, paradoxically, serves as a catalyst for new life. An example of this is the extinction of the dinosaurs, which occurred around 65 million years ago when a giant asteroid struck the planet. This event, leading to the mass extinction of more than 70% of all species, created ecological niches that were subsequently filled by mammals, including our ancestors. Over millions of years, a devastating catastrophe gave rise to new ecosystems in which mammals, such as primates, began to evolve and develop. Processes following strong meteorite impacts often create new conditions for life. For instance, after the Triassic extinction, when many species, including large reptiles, disappeared, dinosaurs flourished on the planet. This demonstrates how the destruction of one form of life can lead to the flourishing of others, sparking evolutionary experiments that continue to diversify the biosphere. Volcanic eruptions, such as the eruption of the Toba volcano around 78,000 years ago, created vast opportunities for the formation of new species, as the ash spread across the land and enriched the soil. As a result, new plants and animals began to appear in ecosystems that were previously unfavorable for life. The destruction of old forms of life opens doors for new ones, allowing nature to restore and adapt. For example, after ice ages, when the climate changed, many species that had perished in harsh conditions were replaced by more adaptable forms of life. This cycle of destruction and rebirth underscores the continuity of planetary transformation, where every end becomes a new beginning. Looking back at the billions of years of Earth's history, we can see that catastrophes not only destroy, but also create. Thus, nature demonstrates its ability to restore itself, showing that in apparent chaos, there is always a seed of order.